Welcome to the edge of possible. Qualcomm is changing the game, driving advances in on-device AI across industries, giving designers new ways to shape the world we live in, and creating tools that can bring our imaginations
Okay, bring it up.
to life.
Add a solar panel array. Yep, there we go.
Whether you're architecting a new world or reinventing the supply chain, Qualcomm is transforming business to bring intelligent computing everywhere. Helping the auto industry design smarter vehicles.
Don't forget, it's date night tonight.
Why don't you find a store that sells simple creamery ice cream?
So you can sit back and enjoy the drive. Qualcomm is engineering human progress, creating a smarter, more connected world for everyone.
跨越人联、物联，迈向万物智联，6G 愿景之旅已然起航。6G 将提供 Tbps 峰值速率、亚毫秒级传输时延，相隔千里的一家人仍能感受到跨越空间的拥抱。在垂直行业，6G 将提供精准定位和确定性通信能力，实现自动化的柔性制造。此外，6G 将支持更密集多样的万物互联。6G 将拥有网络感知能力，超越人眼，认知物理世界。高精度定位和手势识别将真正解放人们的双手，实现随时随地的艺术创作。6G 还将具备原生 AI 能力，从网络虚拟化的集中智能向分布式的网络泛在智能转变。华为6G 团队研发的太赫兹感知成像样机，利用虚拟孔径技术实现了毫米级3维成像。研发的太赫兹超高速通信样机，在220G 赫兹中心频点上实现了室外500米视距下240G bps 超高速传输。光波段有接近无穷的频谱资源，可以融合在已有的光照系统中，特别适用于电磁敏感和超高精度感知场景。华为6G 团队研发的光无线通感样机，实现了3维高精度定位感知和大容量视频传输。华为6G 团队在70G 赫兹频段实现了10G bps 超高吞吐、亚毫米级超低时延的短距无线通信原型样机，整机理论功耗低于560毫瓦。样机采用的先进技术包括快速 Polo 编解码技术、1比特 ADC 过采样技术，基于 AI 预测的波束跟踪扫描算法等。6G 将真正开启万物感知、万物智联的新时代，实现智通万物、惠达千行的人类可持续发展愿景。
在科技创新的浪潮中，前沿科技如同璀璨星辰，焕发社会动力，推动人类进步。6G 是发展未来产业、推动新质生产力的重要战略支撑。它将通信、感知、计算、AI、大数据、安全等多维能力融为一体，通过全域化覆盖、沉浸化性能、多维化能力、平台化网络4大特征，实现更多生产要素的有效供给，加速社会数字化、智能化转型升级。自2023年以来，中国移动协同13家央企及产学研合作伙伴，加快实施未来产业起航行动，围绕6G 领域系统布局，协同攻关原创技术标准制定，强化产业带动及应用培育，取得了显著成效。面对新的历史机遇，未来产业6G 发展进入全新阶段，我们启动夯基、开放与培育3大行动，共赴未来之约。夯基行动，强化技术策源，形成6G 通感算制融合的技术体系，促进重点技术、重大工程与典型场景的迭代创新，加速科技成果转化，筑牢创新发展的基石。开放行动，秉持合作共赢，与3GPP、ITU、NGMN 等国际组织开放合作，推动全球6G 统一标准，协同创新基地众筹众创，共筑开放、包容、协同的标准及产业生态。 培育行动，聚集产业要素，产学研用深度融合，打造移动信息产业集群，培育6G 新型研发机构，孵化新业务及新应用，带动协同创新和融合创新的群体性突破。6G 3大行动将为未来产业的创新和发展注入强劲动能。
我们的演讲嘉宾，今天我们先暖场一下，来一起合个影。Please, dear respected the speaker, can we move to the stage and get group photo?
携手全球合作伙伴，共促6G 创新发展，共创6G 美好未来。
5G 网络作为重要的新型数字基础设施，
Hello. Good morning, everyone. Only 1 minute left. Please turn your mobile phone off or in the vibration mode. We will start 1 minute later. Dear ladies and gentlemen, respected guests, so professors and the classmates, so good morning. I'm Wu Gang. We chair this workshop on wireless integrated sensing and communications. So welcome to the workshop on this ISAC. Today, we will delve into the innovation and application of ISAC technology and jointly explore the future prospect communication and perception integration. Now, let's warmly give the warmly speaker a round of applause. Please allow me to introduce the speaker today. Today. We have online speakers. So first speaker will from the Technical University of Berlin. But he's online, Giuseppe Calais. So, dear Professor Calais, are you online? Okay, so yes, we will test. Here. Okay. The second speaker will from the Jianhua from BUPT. So he's here. And the third will be Professor Chenxiang Wang. He's an academician of the European Academic Science. Okay. And also we have the online the professor talk from the Ahmed Akatib from Arizona State University. And also we have the my colleagues, Professor Yang Ping, but because of the cancellation of the flight, he will give the talk online. Now, we have total 10 talks on this morning, so it will be a long the morning. The 6th talk will be given by Professor Liu Fan. He's here. Please stand and give up. Okay. And we will also have the industry leader from the Ms. Chen Lan, from the chairman of the DOCOMO Beijing. Okay. Please give applause. And also we have the Jin Jing from China Mobile Research Institute. Okay. And also we have invited the Mr. Zhang Zhenyu, also from the Xiaomi. Okay. And finally, we will also have our 6G, the young, excellent speaker, Wu Qingqing from the Shanghai Jiao Tong University. So it's the last talk of this morning. Then after the 10 talks, we will move the panel discussion. The chair will be the Professor Yang. And also we invited the speakers from the Huawei, Guangjian, Wang. Oh, okay. And also the Professor Zhi Yongfen from BPT. Okay. Okay. So we also have very excellent discussion on ISAC frontiers. So please take this chance to listen to the excellent talk from all the speakers. Now, please, Professor Kali, are you online? Okay, so I'm not sure whether the Zoom, the online talk is okay. Okay. If this is some problems on the online connection, so maybe we will move to the next speaker, Professor Jianhua Zhang, okay, who is Deputy Director of the National Key Level Network Switching Technology. Okay, his title will give on the ISAC channel modeling. Let's welcome.
Good morning. Can you give me my? Good morning, ladies and gentlemen. It's my great honor to be here to present some of our recent work, especially about the channel modeling and advanced in 3GPP standards progress. And firstly, I would like to thanks to the Future to organize this special session, and especially from the organizer, Professor Wu Gang, invite me to be here. And so today I would like to talk about the 4 parts. Firstly, the motivation to do this part work, because all of people here, especially today morning session, I noticed there are several topics about the channel model. So I think in the ISAC, the channel is very different from the previous communication channel modeling work. So firstly, I would like to talk about the motivation to do this, and second about some recent progress, and third about how to give a unified channel models, especially we develop a simulator for 6th generation, and finally come to the conclusion. So I think here all of people will agree with why the channel model is so important. All of people know for the wireless peoples, we are facing the very challenging channel, because from the base station to the terminal, there are so many different multipaths. And after the adding of the multipaths, the phase amplitude and Doppler show the dynamic changing. And so we need to model this changing behavior and then to support the research work. So this time, the ISAC channel model already be started, and in standards, I would like to give a historical view about the channel model research work, especially from the, in fact, very, very early time from the Bear Lab, give the Russian channel model, and from the first generation to the 4th generation, we increase the capacity of the MIMO communication. So the channel model also expanded its capability from the time domain to time frequency, and also in the 4th generation, we go to the spatial domain. Especially at the 5th generation, the people know we expanded to the vertical plane. And so we propose like the 3G, 3-dimension GBSM models, and to be used, especially to support the 3D MIMO research work in the 5G standards. So I'm also very honored to be the chairwoman of the ITU 5G channel model drafting group. And so these standards already be used in the 5G. How about the 6th generation? All the people know here we increased several angles, except the triangles we into the 6 angles. So one pillar is about the integrated sensing and communication. So today we go to talk about ISAC. All of people here are very well known why we need ISAC, so I don't spend too much time. Especially, I would like to say, what is the new difference compared to the conventional communication channels? So in order to do the research on the ISAC channels, we need to answer this question firstly. And often the people will ask me a question. What is the difference you need to develop new models for the ISAC? So I summarize there are some new features. Like the first features we can consider like because there are some sensing target, and in order to describe the wave reach the sensing target and reflected by the sensing target, we need to describe its radar cross section. This is a new feature one. So I would like to talk about the RCS, how to describe the RCS firstly. Second is about except the sensing target, there are also some environment around the sensing target. Like if I am a target, there are some walls, some buildings, and how to model the environment object. And in fact, this part will be help to improve the positioning accuracy. Second features about the coupling effect. Like before I appear in this environment and I disappear from this environment, the channel will change. So we will notice there are some dead and birth of the path. So we need to model this part. And finally is about the communication channel and the sensing channel. They share the same propagation environment. So there are some sharing features. So how about the standards activities? I think later the presenter from the Xiaomi will give very detailed description about this part. And in fact, this part of work starts from the Edinburgh conference in 2023 December. And from that time, nearly every 1 month or 2 months, there are meetings until now. In fact, this week, there are a conference in Wuhan. And totally, there are 8 meetings. And we also, as the main importer to the ITU standard, to the security standards, and contributed to this work. So today's slides, I would like to talk about the what is most important part to be considered in the ISAC channel models framework. Firstly, we answer the first new features, that is RCS models. And the second is how to model the environment object. And the third question is to answer the new feature is coupling effect. And the question 4 is about the sharing features between the communication and the sensing channels. So firstly, in fact, in the ISAC standards, the people come to the same consensus is about the how to model the sensing channel is this equation. Sensing channel equal to the target channel plus background channel. So the background channel is similar to the previous communication channel. So we need to be very careful to the target channel. So I think Liu Fan is very familiar with say, oh, what is sensing channel variation? Or it is very simple looks. In fact, it's very complex. Okay. So I go to the second part, how we need study on the ISAC channel. And in fact, we need a sounder to support us to do the measurement. This is our developed sounder, the frequency, the bandwidth, and the detailed specification. So the first question is the RCS features. And this is some experiment or measurement we did in very, very large and chambers. Its size is 60 multiply 30 multiply 30 cubic meters. And we did the different target like the metal and also the UAV and also human, and also we drive a very big car into these chambers to to measure its RCS. And this is the RCS results. We can notice they looks very obviously different from the right side to the left side. Right side is the small size metal sapphire, and the middle side is the human, like me. And to the left side, the vehicular, and also the very large UAV. And you can notice from the right side, it looks more uniform, like circular, and to the left side, it becomes directional. So we need to give models to give this, to capture this variation. So this is our proposed models to also adopted by the standards 3GPP. And its model composed of 3 parts. First part is about A values. A values is a kind of, in fact, the large scale power component. And multiply the B1. B1 is a kind of small scale angular dependent component. Looks like the radiation patterns. And also multiply B2. B2 is a random function component. So you can notice the A, B1, B2 to describe this RCS. So how about this performance? This is the different contributions from the different company. You can notice finally, like the human RCS, the black color is the RCS adopted by the 3GPP. It's nearly minus 1.5 dB, and the yellow color from the BUPT and also others from the different companies. Finally, so when we come to the value, it's a black value. And also, in fact, we give the, like the B1 variation is, errors very small. So second, about the EO features. So why we do the EO research? And in fact, we introduced the ISAC. We want to do the positioning, very high accuracy. So usually we use the radio wave, especially the line of sight, to do the positioning. So if there are some non-line of sight, we can use the B to do the positioning. So to the real world environment, we can have some available non-line of sight paths for this work. So we need to answer this question. This is the measurement we do, and you can notice we use the car as the target and to measure how the part of the power reflected from the environment object. And you can notice from the right pictures, and in fact there are some very strong, like from the fence and the walls, give the very strong reflected parts, more than 60%. So we need to give the accurate models and to describe this environment object. And here we proposed key parameters. It is KEO. KEO described here. You can notice it is defined as the power of EO reflected parts, and then divided by the total non-line of sight paths consist of EO powers. So then we give the H equation. There are EO reflected paths and others non-line of sight paths. And especially we describe how it be inflected by the different materials in our polarization matrix. And here we can notice our proposed EO models can have the very good agreement with the measurement results. And also, in fact, this red line, it is the environment object. It is not line of sight, it is a kind of non-line of sight, will help us to do the more accurate and positioning. So I think this advantage will be very good for the sensing in the future. So third is about the new features, is about the coupling effect. What is a coupling effect? The left picture shows the previous environment without a sensing target appear. And on the right side, you can notice there are car appear. So if there a target appeared, So the environment, there are some paths will be blocked, and there are some new paths will generated. So here we define the sensing target, like the block some environment paths and also generate some new paths. This is a kind of dead and birth effect. So here we give the background. It is the previous environment of the communication channels. So because of some target appear, so some paths will be blocked. So blocked part comes from the new target. And also in the target, in the sensing channels, there are some part will be coupled with the coupled affected. So this is our measurement to validate our ideas. So you can notice on the middle picture is the previous channel impulse response, and if there are some target appear on the right side picture, you can notice some new paths will appeared, and also some sensing target channel will be blocked. So here we give the models how to give the background channels. Here we define a new parameters. It is like a kind of a blockage influence. And also in the target channels, we introduce forward scattering factors to describe this this phenomena. And especially compared with the previous without this coupling effect, we can notice we will increase the channel model accuracy very obviously. So finally, about the sharing features, I notice my time is okay. So between the communication and the sensing channels, you can notice there's some obviously shared multipath component, and on the right side picture you can notice. So we give how to describe these shared features, and especially we quantitatively define as a shared degree. And third, I go to we need unified channel models for the 6th generation. And we know for the 4G, these models is very popular, and for the 5G, we propose the models used in the standards. So how about for the 6th generation? This is unified channel models. We extend GBSM models to support the future 6th generation. And here, except the ISAC, we also consider the extreme large MIMOs, like the spherical and the special non-stationary, and also the race and other new techniques in the same framework. So here is the equation to describe what about the sensing target. So compared to the very simple equation in the standards, it becomes complex. We consider the RCS and the coupling, and also the EO power factor and the sharing scatter. And here we give the simulation framework in the standards procedures how to consider new features, and also in the 2023 June we firstly released this channel model simulator or emulator globally, and also in the last year September we upgraded our channel model generator with the plus. That means we consider all of ISAC standards activities progress and to support the new features. And here is the detail and also validate with our measurement results. So finally, I come to the conclusions. I think the ISAC, the new channel models, there are some totally new features, and also we need unified models to compatible with the 5G. And in fact, there are more future research, like we need more field measurements and also consider the spatial consistency and like the macro Doppler, and we cooperated with the Vivo about this part, and also very interesting results. And for the time limitation, I cannot talk more. Thank you. And okay, this is our, if you are interested, you can pay attention to our web page. Yeah, thank you. Yeah.
Thank you, Professor Zhang, for your wonderful sharing. Your summary on 4 new features of ISAC channel modeling can provide reference for both industry collaboration and on academic research. Thank you again. Now, let's invite the Professor Giuseppe Carri. He is co-chair of this workshop just now because of some problem on connection. Currently, he's online. Okay, Professor Carri, are you ready? So he is professor from the Technical University of Berlin as an authoritative expert in the field of international communication. He will bring us a forward-looking keynote speak on ISAC technology. Okay, Professor Carri, are you ready?
Okay. Hello, hi.
Okay,
hi,
now it's your turn.
Yes.
Let's give applause.
Can you hear me? Can you hear me?
Yes, we can hear you.
Good, okay. And I hope you can also see my slides. Yes, I see that you can see it. Okay, perfect. Okay. So, first of all, thank you for organizing this nice conference. This is a short keynote that I will touch upon a few things. In particular, ISAC from an information theoretic viewpoint and some signal processing problem viewpoint. I'll try to, it's a summary. Okay, so no need to introduce the theme because the whole conference is about these themes and you all know very well what this is about. So let's start with some usually simplified, but somehow is interesting because they somehow reveal some fundamental properties of these problems, so information theoretic models. And the first one is a model that I and co-authors have introduced already since a few years, which is a very simple model. Is a channel, in fact, this is the channel with a state and an input. The receiver wants to decode the information message. So we have an encoder, a decoder, and this channel is also providing some sort of, we say, implicit feedback. The implicit feedback is not really a feedback from the receiver, is, for example, the backscatter signal that comes back from a radar, for example. So when the model is memoryless means that at every time the state is IID independent, and it turns out that the problem is relatively simple to study. So we can define a rate distortion cost triple that is achievable. We say that this is achievable when there exist codes with vanishing probability of error, estimation distortion less than D, and an input cost less than B. So estimation distortion, this distortion function may be mean square error, may be detection error probability, whatever you want to introduce as sensing distortion or sensing error. And of course, the input cost normally in practice represents signal power. So we are interested in determining the best possible rate for a given estimation distortion and input cost. So this problem can be studied, and in fact, we have a full characterization. And here, this is just a super simple example. So the example is just a Gaussian channel where the state is multiplicative, like if it was like a fading channel, for example. And what we see here, we see something very interesting. We see that the optimal scheme can outperform enormously a scheme that does resource partition. So the separation base would, for example, use a portion of the signal dimension for piloting, for sensing, and another portion for communication. And it turns out that, in fact, that the optimal scheme can be, when you work around here, you're essentially sensing optimal and capacity optimal. So there is this trade-off normally is very pointy, which means that clever joint sensing and communication schemes can actually be very close to the best possible rate that the information theory can promise, and at the same time the best possible state estimation error that, say, estimation theory can promise. Then, of course, we have considered more complicated problems. For example, a recent result considers the so-called multistatic sensing, where now the sensing receiver is not collocated with the transmitter. So we model the problem in this way, similar to before, but before the estimator was here, and there was this sort of implicit feedback. Now the estimator is here, is remote. So qualitatively, the main difference here is that to make the problem interesting, the sensing receiver knows the code book, so knows the possible sequences that are transmitted, but doesn't know the message, doesn't know which sequence is transmitted. So then it turns out that one can consider upper bounds and lower bounds. In particular, for the lower bounds are achievable strategies that considers, for example, the case of a blind, which means the estimation receiver doesn't try to decode the code word, treats the code word as a random process. Full decoding, where the estimator tries to decode the code word first, and then knowing the code word, try to estimate the state. And then, of course, there is also a partial decoding strategy. And it turns out that this partial decoding strategy is optimal if a certain Markov chain is respected. So in particular, if the output Z of the estimator is a degraded version of the output Y of the information decoder. So now, moving on in the order of complication, of course, these memoryless models are very far from reality, because normally the sensing is about something that is actually changes quite slowly with time. So we may imagine a state which could be, for example, the position of a target, or who knows, a certain whatever parameters you are interested in, typically changes quite slowly with respect to the rate of communication. And so we need to consider the case of states with memory. And state with memory makes the problem immediately much more difficult. And the reason is that when there is memory, feedback, even implicit feedback through sensing, can actually increase capacity. The problems with memoryless channels are easier because we know that feedback does not increase the capacity of memoryless channels. And therefore, basically, there is not much to do with the sensing cannot really improve the communication. But when the state has memory, in fact, the sensing can improve communication, and this makes the problem more challenging, but also more meaningful. For example, one problem that we have studied in a paper is like a very toy problem. In information theory, we always play with toy problems, and here I call it the beam pointing channel. Imagine that the parameter to estimate is a quantized direction, for example, the beam index in a grid of beams, and the target can be in one of these beams, and in principle, you don't know where is the target. So what happens is that the transmitter must probe these beams and somehow receive either explicitly a feedback or implicitly through a reflected signal to somehow detect the target. But now what happens, right? It happens that you have to partition your power or your time over all these beams. So there is an optimal strategy to explore. And in addition, what we see here, in the case where the state has memory, so the position of the target remains constant for many channel uses and then changes from block to block. You may imagine that the transmitter across a block in which the target remains constant can learn better and better the position of the target and can therefore focus the transmit power in the right direction. So this means effectively, we see here explicitly that although this problem is very idealized, already captures the fundamental trade-offs between sensing and communication. And when the state has memory, we see that not only we can do joint sensing and communication, but the sensing can improve communication, as in this case. Then finally, the last information theoretic model I want to touch upon is the case where the sensing channel and the communication channel are completely distinct, so there is no feedback, simply are driven by the same input. So we have a transmitter that is transmitting to some receiver, but with the same input wants also to estimate something else. And in the Gaussian case, so this is the linear Gaussian model where the channels are two matrices and the input signal is a space-time code word, if you want. It turns out that an interesting thing to do here is to study the role of something that we call the sensing mutual information. So in general, in communication, we are interested, the mutual information for this channel, which will be the mutual information between X and YC given HC. This is the classical quantity that we look in terms of communication rate. But if we exchange the role of X and H, in fact, this is the mutual information between the received signal at the sensor and the channel, at the sensing channel, given the transmit signal. And it turns out that, in fact, this sensing mutual information, first of all, it coincides with the mutual information with respect to the parameter we want to sense. So when the sensing channel is a function of a random parameter, for example, in the classical radar problem, this may be the function of angle of arrival and range and Doppler shift and things like this. So it turns out that this is the same. But what is interesting here is that one can find an operational meaning to this sensing mutual information. In fact, for any distortion function, which means for any error, not just mean square error, it could be like Hamming distance, whatever error the function you want to find. And any possible sensor that tries to estimate theta from ys knowing x, it turns out that the average distortion is lower bounded by the inverse of the rate distortion function for the parameter calculated in the sensing mutual information. So this is a universal lower bound that in a certain sense is more powerful than the Cramer-Rao bound, because we know that the Cramer-Rao bound works for mean square error, but if I have something else, in fact, the Cramer-Rao bound is not meaningful. As a matter of fact, one can show something even more, that when this distortion metric is the so-called log loss. So for example, suppose that we have a classification problem and your sensing needs to classify objects in a landscape, like for example in imaging. Well, it turns out that the sensing mutual information is precisely the average log loss is connected precisely to the average distortion in terms of log loss. So it has a very interesting meaning. And one thing I want to conclude is that, okay, with a little bit of more math, which is taken in this paper, one can show that for this linear Gaussian model, it turns out that while the communication mutual information is maximized by when X is a Gaussian, follows a Gaussian distribution, the sensing mutual information is maximized when X yields a deterministic sample covariance. So when essentially the X is such that this sample covariance is constant for every code word. And this happens when X is a family of unitary matrices. So one can visualize these things in this way. When we have the communication optimal signals look like essentially Gaussian vectors, and sensing optimal signals look like unitary vectors. So they are essentially point on a sphere. We call this the deterministic random trade-off. And in other words, this may be a good criterion to design code books that are good for communication, but they are also good for sensing. Okay. Now I'm going to touch upon a few signal processing problems. The first one is very much inspired to this beam pointing channel. So here we have a base station that does beam tracking, and we want to use beam tracking. We want to use radar to do beam tracking. So of course, depending on the architecture here at the base station, this may be very simple or very complicated. If we have a fully digital array, right, basically we have essentially a MIMO radar that is shooting in one direction and receiving, and then we can simply estimate the angle of arrival and use this in a trajectory tracker to predict the next angle, and therefore. But of course, for example, for high frequencies, often we don't use a fully digital architecture. We use, for example, beam steering in the analog domain, or maybe using an RIS or something that can be controlled, like a controllable reflector that somehow steers beams. And therefore, depending on the architecture, the problem may become much more complicated. And in particular, for example, when we have only one RF chain, so we have essentially no possibility to have a multidimensional observation, and therefore techniques like, for example, angle of arrival estimation, even in the beam space, cannot work. Then we find that, for example, training a neural network that somehow learns the dynamics of the motion yields some advantages. So, for example, this is an example where we have a road trajectory, like this is, for example, a roundabout, and there are streets like this, and this is an example where this is along a trajectory. We have the oracle, where is the rate so the base station is here, and the vehicle move like this, and the vehicle move in a strange way. So it stop and go, and then has this abrupt change of direction. And the oracle has always the perfect pointing, and we see that, for example, our tracker, even just with a single RF chain, is able to follow the oracle with maybe some spikes. These negative spikes are due to the fact that the tracker may lose momentarily the right position, and therefore suffers from gain loss in this. The beam is not perfectly pointed, and this typically happen at this point where you have like a sharp transitions of the velocity vector, so the tracker has difficulty in following. Another problem that we have looked at is the problem of extended targets. So here we have extended targets that are essentially formed by clusters of microscatterers that are typically non-distinguishable. So we cannot really estimate the individual points that form the extended target. And we also have, multi-static and mixed near and far field. For example, we have trajectories that may be all in the near field of the transmitter, and in the far field of the sensors, we have trajectory that starts in the near field of the transmitter and then migrates, etc., etc. So we have all these situations. And here the strategy is that since we do not know a priori if the near field or far field, what we do is we do the detection of the target as some sort of coarse detection, assuming far field, and then a refinement using near field, say, precoders, because when the target is detected to be in the near field. And long story short, so the coarse detection is based on essentially radar techniques, so using the CFAR and the likelihood function, and slicing the likelihood function and finding peaks in the parameter space. Here, the parameter space is angle and delay, but it could be a multi-dimensional. It could be angle, delay, and Doppler, or two-dimensional angle if you have elevation and azimuth. And then this is the beam focusing when the target is identified to be in the near field. And what happens for these point clusters is that if we use far field precoders while the target is in the near field, we see basically this sort of low resolution bubbles. And when we focus and we actually exploit the knowledge that the target is in the near field, we can actually resolve points. You see that we see more details in the target. And so one can, for example, do these things for which appropriate fusion of near field and far field allows target detection probability that is close to 1 along the whole trajectory, while if you use only one of the assumptions, this is not so good. Another thing is that when the target is detected to be in the near field, then one can do beam focusing and therefore improve the achievable rate. In particular, here we assume a target that has an antenna in one point, but of course the target is diffuse, so you don't know exactly where to point, and so the beam focusing, in fact, is designed such that we do not focus in a single point because we do not know the exact direction. You know this bubble, and therefore you focus like here. You create like this region of high signal with a certain shape. Finally, how much time do I have? 5 more minutes.
Hello, you have been behind the schedule. Or maybe 3 minutes.
So I'll try to be brief. Finally, I want to say something about the positioning in a cell-free network, which is also a form of sensing. So a cell-free network is a network where every user is served by a cluster of user-centric radio units that are in the vicinity, and it's self-free because when the user moves, this cluster changes. In a cell-free network, because we do not have the sectors, the cells, the cell boundaries are not pre-assigned, otherwise the network will be just a cellular network, a small cell network, and we know very well what to do. In a cell-free network, there is a problem in users that randomly access the system because you don't know where they are. They can be anywhere. And so how do you allocate pilots, allocate the user-centric cluster, and so on and so forth? And also in the positioning. In the positioning, precisely because these users are idle and then they become active, and we would like to localize them very quickly. So in particular, we have studied, the so-called the two-step ratch. So the idea that a random user for low latency would just simply send the preamble and send data right away without waiting for the permission, and the system simply acknowledge. And then, of course, if in this data there is a request for connected traffic, then the acknowledge will contain a message that says that allocates some resource, and then the user is connected, and so he keep using a certain resource for many slots until it releases, and then it goes idle again, and so on and so forth. Otherwise, if it is a very short packet communication, this is just a single burst of data, and that's it. So in this case, basically the structure is that periodically, all the radio units all together send at the unison a clear to send signal, so a trigger frame. This trigger frame tells all the user the next frame is random access. So the users who want to access the channel will send in this random access these preambles. And then we have this processing, the fast acknowledgement, so we have the super low latency, and then if the users have more data to transmit, well, basically they are given the resources here, and then they become connected. So what we want to design is a scheme that users transmit in the random access channel, the system detects them, estimates their channels, allocate a user-centric cluster, is able to respond within like 1 millisecond using beamforming from multi-point, respond with an acknowledgement, and in addition also localize these users as precisely as possible. And it turns out that we can use the following fact. The network is distributed, and therefore the so-called large-scale fading coefficients from a user to the radio units can be very different. So in particular, you may imagine that if you collect all the antennas of all the radio units in a big vector, this vector contains blocks with different strength, because maybe this one is short and therefore the user receives a high power, this one is receiving a high power, but maybe this one is a very long path and is receiving a low power. So we have this so-called large-scale fading coefficient profiles. And effectively, if you think for a second, every profile corresponds to a position. Not uniquely, but somehow you can get, intuitively, you can say, if you know the profile, you can, and you know the position of the radio units, which is known, you can locate the users. So it turns out that, I will cut the story very short, but it turns out that the problem can be modeled in this way. So we collect all the preambles in these codebook matrices, and users in different positions have a different statistics. So these are the channel vectors with these different profiles. And it turns out that at the end, the scheme has this structure for which we are interested in knowing which of these preambles. So if I some of these columns here, or these code books, are active, others are not active. We want to detect the active users, so the active columns here, and the corresponding channels. The corresponding channels are the rows of this matrix corresponding to these indices, because these are the channels of the active user that can be used to do beamforming in the reverse direction. So this can be done using a variant of the approximate message passing algorithm that we call multi-source AMP, which is this extension to sources of different statistics that has the advantage that can be analyzed in closed form, and therefore we can basically analytically also calculate the corresponding denoising function, etc., etc. Let me give you an example. This is a network with 16 regions and 12 radio units. 16 regions because we allocate access subcode to every region. And this is with the very classical path loss models and the transmit power, etc. This is where the system would operate. The system can operate here, for example, at the probability of misdetection and probability of false alarm, both around 10 to the minus 2, which is pretty good. And we compare the estimation of the channels with respect to a gene-aided system that would use MMSE estimation, assuming that all the users, the active users, are perfectly known. So they're all like non-pilots. And we see that the AMP without this assumption and the gene-aided work relatively close. So this provides a very good channel estimation. But also, and here we go into the sensing condition, we can extract from these AMP statistics, we can construct a likelihood function for the position. And therefore, we can also estimate a refinement of the user position. And this is an example for this distance-dependent path loss. So this is a very simple case where the path loss is deterministic and depends on distance. We see that our scheme provides, this is the CDF of the channel estimate, of the position estimation error. This is the absolute position error. And the oracle is basically simply the quantization to the closest grid point, because this is a discrete detection, and so we the position are estimated on a discrete grid. So it's essentially almost like a gene-aided. Now it turns out that reality, the path loss, the large-scale fading coefficient are everything but radial function. They're not just distance dependent. These are statistical models, but when you do ray tracing on a real environment, for example, here the blue points correspond to the position of the radio units, and then the red shapes are buildings, and the green are trees. And then we have run ray tracing, and so for every transmitter, we get the so-called radio map, which is precisely the path loss function with respect of all the points on the coverage plane with respect to the transmitter. And so we see, for example, that the path loss function for this transmitter is absolutely not radial, has no radial symmetry. So these things for which the path loss is 1 over d to the alpha is a complete false in reality. And you see that they have a very strange structure. So the question is, can this scheme still work when we use realistic path loss function that do not have these, say, distance-dependent, so essentially when the signal strength is not a one-to-one function of the distance, because, you know, when it is a one-to-one function of the distance, it's easy. Signal strength means distance. Distance you can do essentially implicitly triangulation, so it works. But when we are in this case, does it work? Well, what we do, we take the real from ray tracing, the large-scale fading profile for every pixel. This is a vector. In this case, we have 9 base stations, so it's a vector of 9 components. And then we can cluster these large-scale fading coefficients. And then we find these cluster regions. This is a clusterization using k-means plus Lloyd-Max algorithm. This is in 9 regions. This is in 18 regions. So basically, these are the regions of points that have similar large-scale fading coefficient profile. And then we can apply the same algorithm as before, but now we use these regions. And so here is an example where the blue point is the true position of the users, and the yellow points is the estimation for a certain clusters. And here is the CDF, and we see that, for example, in this case, these squares are 500 by 500 meters, and here with probability, with 80%, we can locate these users with less than 10 meters error. And this estimation is purely based on signal strength through these algorithms. There is no requirement from synchronization, no requirement for angle of arrival, line of sight, time difference of arrival. So because this is random access. These users are idle. They transmit, and they are immediately detected, channel estimated, and located quite precisely. And therefore, for a cell-free network, this is interesting because you need to do this very quickly in order to allocate a user-centric cluster to these users. Otherwise, they cannot communicate. And there is no base station that helps you. It's a cell-free system. So with this, I'd like to conclude, and I hope that, I gave a little bit of an overview of a current work, and that touches both the information theoretic aspects and this signal processing aspects. And of course, this is sensing very much oriented to helping communication. Sensing in a different way, like for example, imaging the environment is not really included in this talk. And with this, I'd like to thank you for your attention.
Thank you. Thank you, Professor Kari, for your wonderful talk. Your summary from both the information theoretical and the signal processing on ISAC, I think is very wonderful talk. Okay, so it's very early morning, so we will move to the next speaker, who is Professor Chenxiang Wang, who is an academician of the European Academy of Science and Attribute Fellow, and who will give a talk on 3D continuous space radio channel modeling for ISAC.
Thanks for the chairman's introduction, and thanks for the invitation. Ladies and gentlemen, good morning. So my topic today is still channel modeling, but I would like to talk from a quite a different perspective, talking about the future. The future trend for 6G and even beyond. So the title is 3D Continuous Space Radio Channel Modeling Theory for 6G and beyond. So 4 parts. The first one is, evolutionary trends and challenges for future wireless channel research. So future wireless communication networks certainly include, 6G, beyond 6G, military communication networks, UAV communication networks, and these future wireless communication networks have the following main features. First of all, they tend to cover, space, air, ground, sea, global coverage instead of only focusing on terrestrial communications. Second of all, not only the users can move, but the base stations tend to move continuously as well. For example, satellite, UAVs, ships, and vehicles can all serve as moving base stations. And we are going to deploy some new communication technologies such as, ultramassive MIMO, ISAC, race, holographic MIMO, and so on. And then future wireless channels tend to be, the so-called 3D continuous space radio channels. So in Chinese we call 连续立体全空间无线电信道. And the key features are, you can see, so the propagation environment tend to be cross-layer, so not only, in one layer, and multi-scale, so tend to be very large scale. For example, from satellite to sea communications, so very large distance. This is quite different from traditional terrestrial communications. And the media is very complicated in homogeneous media, and even when we talk about the channels, could cover, multi-cross media. Therefore, understanding the underlying electromagnetic fields and characteristics for 3D continuous channels are necessary. On the other hand, the antennas could be deeply coupled with the underlying propagation environment. For example, when we talk about ultramassive antenna array in shortwave bands, this could, range like a few kilometers if we have 100 antenna elements. Therefore, we have to focus on the so-called generalized radio channels, and that will integrate the transmitter and the receiver antennas with wireless propagation channels properly. So traditional wireless channel modeling will focus on wireless propagation channel, and future, channel modeling have to consider the joint modeling of transmitter, receiver antennas, and propagation channels. So there's a necessity to acquire 3D continuous space channel state information. There are three main reasons. First of all, as I mentioned, the base station and the user tend to move continuously. Second, ISAC needs to obtain channel state information at any point in the full space in order to properly design ISAC sensing and communication systems. The third reason is the so-called channel map. So traditionally, when we do channel estimation, we need to obtain instantaneous. We need to send the pilots to obtain instantaneous channel state information. But for 6G and beyond, antenna elements tend to be, pretty large, and also we have many more users, many more systems, and many more networks. Therefore, acquiring instantaneous channel state information is not realistic. So our idea is to propose the so-called channel map. We move, let's say, traditional system design challenge to the channel research, and we construct channel map that can greatly reduce the complexity of system design by acquiring environment-related channel state information in advance. And for radio channel modeling, as I mentioned before, that's the joint modeling of transmitter-receiver antennas and wireless propagation channels. Okay, so there are at least 4 research challenges regarding 3D continuous space radio channels, because one is channel categorization and modeling. There's no such theory before for 3D continuous space radio channels, and also capacity analysis, either channel capacity or system capacity. The third one is the general antenna design, that is including transmitter receiver antenna and the underlying propagation channels. Finally, it's a channel map enabled system design and optimization. As we know that, there are 2 fundamental theories for wireless communications. One is, electromagnetic theory proposed by Maxwell. Another is, Shannon channel capacity theory. And the wireless propagation channel modeling theory and antenna theory are the 2 links bridging these 2 fundamental theories. But traditionally, from 1st generation to 5th generation, these 4 theories are more or less independent. Okay? For example, traditional propagation channel modeling theory and information theory, they are based on discrete space. I will explain in more detail afterwards. They only consider some antenna parameters, but not all antenna parameters. Therefore, few, 1, 2, 3 are separated, and 2, 3, 4, are separated as well. And for traditional antenna theory, they does not fully consider channel statistical properties. Okay, the impact of all antenna parameters on the underlying channel statistical properties, and also, capacities as well. So, therefore, the solution to solve the challenges of 3D continuous space radio channels are the so-called electromagnetic information theory. Basically, we construct the EIT that will integrate these 4 theories together. So the second part is, we propose a new theory of, solving the problems facing, 3D continuous space radio channel models. So what's the key difference between traditional discrete space propagation channel model and the continuous space electromagnetic channel model? First of all, for traditional discrete space propagation channel model, we trace electromagnetic waves as rays, okay? And we consider the multi-path effects of signals during propagation. And for transmitter receiver, we just consider, it's a single point, transmitter and single point receiver. And for the scattering environment, normally we use cluster-based channel modeling. So we consider there are many clusters in the scattering environment, and within each cluster there are many rays. Okay, therefore these are completely discrete. But for continuous space EM model, we trace EM waves as fields. And that's actually the real propagation. And we consider the coherent behavior of EM waves in complicated environments. And now the transmitter receiver, instead of considering, single points, we consider transmitter receiver as actually current density electrical field strength of continuous region is volume instead of single point. For scattering environments, we consider, scattering potential function for continuous region volume. So it's kind of a volume, it's an area instead of, clusters with, discrete rays. So that's the main difference, right? So what's the key advantages of such continuous space channel model? For traditional, discrete space channel model, because of, transmitter receiver is a single point. For example, if we want to, construct the so-called channel map for this, lecture hall, yeah, we only model single point. If we want to cover, this lecture hall, we have to, cover all the points, right? And in theory, the underlying complexity is infinity. But now, for continuous space channel model, we model the receiver as kind of, area. It's a region. We consider its volume. Therefore, we can model all the points within this volume immediately. This is much more efficient channel modeling in comparison to discrete channel model. Okay. Right. So this is the underlying channel model we have constructed, and due to time limitation, I won't go into detail. And we have considered the antennas, for circuits, and we have, current density and electric field strength as the transmit signal. Transmitter and the receiver. Okay, so now let's show some results. First of all, we compare 4 different channel models. Clearly, the most complicated one is continuous space radio channel model, and then we further reduce that to EM channel model without considering antennas, and then we further reduce that to discrete space radio channel model without considering continuous space, and then the traditional one is discrete space propagation channel model. So we compare these 4 channel models. Clearly, you can see, for continuous space channel model in comparison to discrete space channel model, the correlation of the received signal is much lower. This is because, for continuous space channel model, we consider a large range of spatial distributions and more complicated, more richer propagation environments. Okay, so this is comparison continuous and discrete. And comparison, between radio channel models and propagation channel models. So clearly you can see, because radio channel models consider the mutual coupling effect between adjacent receiving poles, therefore the spatial cross-correlation function is larger than that of propagation channel models. And the temporal autocorrelation function is non-stationary because we have considered, the long distance movement. Okay, we have done the so-called continuous space channel measurements for 28 GHz for the moment. The bandwidth is 200 MHz, and you can see the spacing is about 0.1 meter per measurement point. Okay, and we further analyze, system capacity for the 4 different channels. So I show a figure why the proposed channel model is much more efficient. Okay, and for traditional, discrete channel model, if we assume the transmitter is fixed and the receiver have to move for channel measurements and for traditional discrete space channel modeling. But now for continuous channel model, we don't need to move the receiver. Okay, we just increase the radius of the underlying channel model. Okay, so clearly you can see when the radius is larger and larger, the complexity, or let's say that the underlying channel model is much more and more efficient, but the accuracy will be somehow reduced. And we can assume an underlying threshold. For example, we compare channel measurements with the proposed channel model. We assume the accuracy threshold is 85% or 90%, and then we can calculate the radius of the continuous space channel model. Okay, but within the whole space, any points, any channel state information within the whole space can be obtained immediately. Okay, and we can show by theory, by simulation, by measurement, continuous space channel model, the capacity, the system capacity is much larger than traditional discrete channel model. Okay, so then this has great significance for future communication system design if we compare continuous space and discrete space channel model. The first one is antenna design optimization. Okay, traditionally we fix antenna. So after you have designed the antenna, and when you use that for communication system, you just use antenna array, either is a linear one or square antenna or whatever, okay? But for continuous space, we don't consider a certain antenna array. We consider its current density, electric field density. We assume it's a volume, okay? We assume when we calculate the underlying system capacity, we actually consider the optimum design of antennas, okay? So the second one is rich scattering environment construction. Yeah, when we consider a 3D continuous space channel model, we actually consider rich scattering environment. Therefore, in future, we can, utilize RIS, communication-friendly materials, and ultramassive MIMO, holographic MIMO, and so on, to form rich multi-path propagation environments. The third one is orthogonal transmission scheme design. Okay, I won't go into detail. There's also significance for channel measurements. When we construct channel map, we know that channel measurements are always discrete. But how many channel measurement points do we need in order to construct a channel map? We don't have any theory, before. And now, actually, with this continuous channel modeling theory, we can, supervise, or we can give a lot of guidelines for future measurements. Okay, for channel map construction, I won't go into detail again. So the last part, just to quickly show the 6G channel simulation platforms and the underlying applications we have done within our team. We have proposed, the so-called pervasive channel modeling theory. So far, we have constructed, GBSM, 6G pervasive GBSM channel simulator. We have released 3 versions, received a lot of, quite good feedback. And now we are constructing pervasive retracing channel simulator. We haven't released because we need a company to reverse MATLAB to C++. And now we are developing a 6G pervasive intelligent prediction channel simulator, trying to collaborate with companies to build a channel emulator as well. Of course, we have a lot of channel measurement database. For platform, we have constructed a quite basic 6G digital twin online or real-time channel simulation platform, and we are trying to apply the constructed channel simulation platform to a lot of system design and optimization applications. This is the constructed digital twin online channel simulation platform. I won't go into detail today. And this is, based on channel map, we can apply to channel prediction, channel estimation, signal processing, decoding, beam alignment management, user scheduling, access, wireless positioning, and so on. So these are some of our published papers related to today's talk. If you are interested, welcome to read our papers and give some comments. So that concludes my talk. Thank you very much.
Thank you, Prof. Wang, for your wonderful talk. Your insight on 3D continuous space channel modeling is really refreshing. Let's welcome the next professor, the speaker, the Professor Ahmed Aktib from Arizona State University, who will give a talk online. So, Professor Ahmed, Are you online? Are you ready?
Yes, I'm here.
Some
Can you hear
delay.
me?
So, okay. Yeah. Now it's your turn. So, welcome. Let's welcome the Professor Ahmed, executive, to give the talk. Okay. Please share your screen. Okay. Can you hear me?
All right. Yes. Just one sec. Okay, I guess you can see the, okay, I can see the slides in your screen now. All right, so thanks everyone for attending, and thanks for the invitation. So today, there was a suggestion that I talk about our data sets, DeepSense and DeepVerse, so I tried to prepare some slides to give an overview and also how to get started using these platforms. So this is work done jointly with my PhD, master, and undergrad students, and has been funded by NSF and industry. All right, so I would like to talk about, again, two data sets that we have built over the last 4 or 5 years. So DeepSense, DeepSense 6G, which is a large-scale, real-world, multimodal sensing and communication dataset, and DeepVerse 6G, which we actually just released yesterday. And it is a digital twin version of DeepSense. So it is a multimodal sensing and communication dataset, but it is basically high-fidelity synthetic based data. And it includes also modalities such as vision, LiDAR, radar, and communication. And some of the scenarios are digital twin replicas of the scenarios we have in DeepSense. All right, so let's start with DeepSense. And again, as I mentioned, it is a large-scale real-world dataset based on real-world measurements. That includes synchronized data from multimodal sensing and communication. So I quickly go over motivation, overview of the data set, and some example applications, and also how to get started if you are interested. Okay, so if we look at the future communication systems and sensing systems, we envision that communication infrastructure and also users will be equipped with multiple types of sensors, from vision, LiDAR, radar, communication, also wireless sensors. And these sensors would provide different types of information, from position information, orientation, shape, mobility patterns, EM characteristics even, and more. And all this information could be very efficient and very useful to aid and support the different communication system decisions for beam prediction, channel estimation, codebook design, user association, scheduling, and so on, for different types of communication systems, from massive MIMO, mmWave MIMO, intelligent services, and so on. And especially that as we go large in number of antennas and higher in frequency bands, channel acquisition becomes more difficult. But in the same time, these systems become more and more dependent on the user location and the environment and the scatters and so on. So, which basically increase the value of having the sensing information to support these systems. And also these larger antenna arrays and higher frequency band systems, they also provide a lot of values for sensing, from spatial resolution, range resolution, and so on, which could also support eventually sensing. And also the signals could be used to perform different sensing functionalities. Okay, so sensing and communication, and when I talk about sensing, I mean generally multimodal sensing and communication. They can support each other, and they also may need to coexist in terms of compute resources and so on, radio resources and so on. So in order to really do research in these directions, we need to have a data set that, especially if we want to do machine learning and deep learning research, so we need to have a data set that was coexisting data from sensing, from all these different sensing modalities, as well as communication, so that we can study how sensing can help communication, how communication can help sensing, how can they coexist, and so on. And that was the motivation behind building a DeepSense dataset a few years ago. And DeepSense is essentially a collection of datasets that are so based on real-world measurements. And these datasets are every one of these datasets has basically coexisting data from these different multimodal sensing sensors, in addition to communication. So far, we have around 44 scenarios, and that cover different applications from, or use cases from V2I, V2V, drones, RIS, and so on, indoor and pedestrian kind of movement, and with around 1.5 million multimodal data points. And these data sets are structured in, so basically we have what we call deep sense testbed. So it's tried kind of to standardize the way we are defining these testbeds so that we can scale to different use cases. And every dataset testbed has a number of units, and every unit, for example, a base station unit, a user unit, a mobile device unit, and so on. And every unit has a number of sensors. And essentially, the way we structure this data is that we collect the data from all units in a synchronized way in post-processing, so that eventually, at every sampling time, you have data from all the units with all modalities that are available. So that everything is synchronized, and now we can start looking at how we can use different sensing to help communication, or the other way around. So, you can check these different testbeds on the website with clear description as well as the scenarios on the DeepSense website. So this is an example scenario where we have a V2I use case. So this visual data is captured from a camera installed at the base station. And one of these basically vehicles is a user vehicle carrying a transmitter, and the base station is collecting the received signal. So this is the beam with this is a 60 gigahertz millimeter wave communication channel, where we have a 64 beam codebook that is used to serve this user. So these are the 64 beams that power measured across every beam. We do exhaustive search at every sampling time as this vehicle moves. We also have collect LiDAR, 3D LiDAR, and camera information, as well as radar installed at the base station. So that's an example scenario. And then this is another one where we have a V2V. So that's the vehicle-to-vehicle use case where we have a transmitting vehicle and the receiving vehicle. We collect, again, radar from 4 sites at the receiving vehicle, and as well as 3D LiDAR, 360 camera, and wireless information. So here the wireless is communication information is mainly beam information. We have also more scenarios actually contributed by other universities in DeepSense. So DeepSense is, we hope to kind of make it a community dataset where any research group can contribute to the dataset. So we basically define more like the standard of the way we define we try to standardize the way we define the dataset, and then we work with any groups that's interested in contributing with the dataset to transform the dataset into the standardized way, so that basically all the datasets in DeepSense have the same exact structure, even if they are contributed from different testbeds. So that's an ISAC or sensing and communication scenario that is contributed by a Polyme University in Italy. It has radar information and communication, and that was also used to do some interesting research on the coexistence between communication and radar. So of course, if a group contributed with the scenarios, then basically we ask the users of the scenario to cite their paper. So credit is reserved in here. All right. So what we can do with the DeepSense dataset, since we have coexisting data from sensing and communication, multimodal sensing and communication, and it's also available in large scale. So we believe this could be very interesting in supporting different machine learning for communication applications, or in general communication algorithm development for beam prediction, tracking, blockage prediction, handoff, and so on, as well as sensing application in ISAC and positioning, as well as even object detection classification. And since we have a large data set collecting from different sites, so this could be also interesting for different machine learning, basically directions in transfer learning, fusion learning, data fusion, and more. And we hope this enables the development again of the different applications, as well as facilitating benchmarking and comparison. That was kind of an important consideration when we were building and publishing this data set until today. So this is an example task. We also defined some of the important tasks on the data set where groups can contribute to basically these challenges and get listed. So this is one of the tasks for multimodal beam prediction, and we have actually submissions, and we still have many groups submitting till today. So So again, encouraging and everyone interested to take a look and let us know if you have any interest. So these are different also example applications that we have been and other groups have been working on using the DeepSense dataset, and you can find these applications and publications on, in addition to their code and datasets and everything, on the DeepSense website, on the publications. So that is an example or a demo that was done using DeepSense for using visual data and position information to do beam tracking without using any wireless communication resources. So saving and enabling saving wireless resource, and enabling the scalability of MIMO systems. This is another application where radar information was used to do proactive blockage prediction in millimeter wave. So blockage is a big challenge for millimeter wave systems. And if we can proactively predict these blockages before they actually block the links, the line of sight links, then this can enable the network to make some proactive actions, for example, handoff or beam switching. There are also more applications and datasets for drones, V2B, and also more recently we have been publishing more scenarios, what we call distributed sensing and communication, where we envision that in the future, because of the difference in their coverage range between sensing and communication, then between different sensors, for example, cameras, LiDAR, radars, they have different range compared to communication. So we envision that eventually we'll have maybe network of distributed sensors supporting the communication network. And so we have been also building and collecting some data and scenarios for this use case, where we have distributed sensors. And then this raises many interesting questions on how this data should be communicated, and maybe environment semantic extraction with goal-oriented for some end communication task, and because eventually the data traffic of this sensing information become a challenge, and how to solve that and so on. So it's kind of a very interesting, it opens interesting directions again for distributed learning and many more. All right, so if you are interested in these data sets, you can check the website, check the different scenarios we have, and we have also tutorials on how to generate the different modalities in the dataset, as well as many actually demos also and applications that were done using the dataset. Yeah, and let's know if you have any questions. So that's for DeepSense. And also, again, let's know if you are interested in contributing dataset, and we'll be happy to work together on transforming it to a DeepSense format and publishing it and adding your citations. So another dataset that we have been also working on for a few years, actually we just released yesterday, is what we call DeepVerse 6G. And vision for DeepVerse was to achieve two objectives. One is no matter how many data points, real-world data points we will be able to collect, or real-world measurements, we think that there will always be a need for synthetic and high-fidelity synthetic data to basically pre-train machine learning models and augment data and so on. So we wanted to build a kind of a synthetic version of DeepSense that still has all these multimodal sensors or sensing information, but also has the communication. And then now, since this is synthetic, we can have like more information about communication, like all the way to the channel parameters and channel complex channel matrices and so on. And then another also a motivation was digital twin, that in many cases you would like to, many interesting applications on having a digital twin to the real world environment, and then looking at how to merge data from digital twin site-specific data generation on different digital twin applications and so on. So that was the motivation behind DeepVerse. So again, digital twin could be interesting in many applications for building realistic site-specific datasets to pre-train machine learning models, and as well as even making real or near real-time decisions for real-world communication systems. So that this digital twin could be living maybe at the edge or cloud, and could support some near real-time or non-real-time decision and priors to the communication system that can help in, for example, narrowing down the search space for beams, or providing some prior about the large-scale channel statistics for CSI compression or pilot design, and many interesting applications, localization and sensing and so on. Again, so it could have applications across the stack. So I may probably need to move a little bit fast for the time, but if you are interested, you can check this magazine paper that we go kind of in detail into digital twin and how we envision, especially what we call real-time digital twins that keep learning and adapting to the real-world environment and provide real-time kind of or near real-time priors to the communication systems. Skip this for now. So with this motivation, we built Deepverse, again, as a digital twin research platform where we pre-generate what we call Deepverse scenarios with vision, LiDAR, radar, and position information. So these are all digital twin data. And then using, and then similar to our other data set called Deep MIMO. So you pick a scenario from Deepverse, and then you define the parameters that you would like for the communication and radar. For example, the radar waveform, the different parameters in the radar waveform, as well as the different parameters for the communication system. For example, the antenna configuration, orientation, polarization, and so on. And then, so with these parameters, the Deepverse generator generates a data set that you can then use to do, to kind of explore the different research directions you're interested in. So ISAC and how multimodal sensing could help communication and communication channel estimation, for example, and so on. So this is an example scenario in Deepverse where we have the real-world data from DeepSense, scenario 1, and the corresponding digital twin replica that we built in Deepverse. So it's called Digital Twin 1, DT1. And this is not just about modeling the texture of the buildings and the visual features, but also we have been working hard on modeling the wireless and the different wireless, basically, components. For example, we take the array, the millimeter wave arrays that we used to collect the real-world data in DeepSense to the anechoic chamber. We measure the beam patterns, and then we incorporate these models in the digital twin. So we have been kind of putting a lot of effort in the calibration of the two data sets across the different modalities. And this is an example. So this is the scenario that I just showed in on the top you see the digital twin, and the bottom you see the real world. Again, across vision, this is LiDAR digital twin, and this is a radar digital twin. And then, of course, here the advantage of the digital twin is that we don't have noise, and so you can study, for example, the performance across different SNRs and so on. This is another scenario that we built where here we don't have just our transmitter vehicle, but we also have the other vehicles in the environment modeled and incorporated in the projected on the digital twin. So it's a multi kind of object scenario where we again model visual data, LiDAR data, radar. So that's the digital twin. That's the real world. So this is range Doppler, for example, range angle, and we have the IQ data for actually real world and for the radar for IQ for real world and the digital twin. So in addition to these digital twin scenarios, Deepverse has also multiple what we call virtual world scenarios. So these are not like digital replicas to DeepSense scenarios, but they are just generally multimodal sensing and communication synthetic datasets for different cities and different also indoor scenarios. So we hope this enables a lot of interesting research directions in ISAC, positioning, multimodal sensing, and communication, machine learning, and more. And these are some kind of quick applications, a few slides quickly that cover some of the applications we have been looking at on, for example, beam prediction, digital twin aided beam prediction, where we train machine learning models offline on digital twin site-specific datasets to predict beams, and then we measure this on the real world and see how much performance we can actually get without any fine-tuning, and then how can fine-tuning further improve the performance. We looked also at some problems like ISAC beamforming design using digital twin, and interestingly, even a very simple information like whether this user is or the sensing target is line of sight or non-line of sight. This could be very efficient for the algorithm design to know like how it should design the beam to basically adapt to this line of sight or non-line of sight configuration, and this makes significant improvement in sensing SNR, for example, in this case. So this is a paper that was presented last at Silomar. We also looked at how digital twin could help in CSI compression, in positioning, improve positioning, and reduce the amount of drive tests that's needed by relying on digital twin RF maps to pre-train these positioning algorithms. Also channel estimation, where digital twin could be very interesting in providing priors and channel state large scale channel priors that could help, for example, reduce a subspace where we are estimating the channel, and saves a lot of pilots and CSI feedback overhead. That's a paper that will be presented in the next ICM-LCM, so in the next month. And yeah, with that, so basically deepversygg.net is now available. If you're interested, you can check the website. We have different scenarios. We have also a tutorial that goes in step-by-step on how to generate data, as well as a demo that we just released again yesterday on ISAC beam prediction using Deepverse. And let us know if you have any questions. So with that, I'd like to conclude. So thank you very much, and looking forward to any questions either here or offline over email. Thank you.
Thank you, Professor Ahmed, for your wonderful talk, especially your from deep sense to deep words. Okay, because time limitation, we go to the next speaker, who is Ping Yang from the UESTC Chengdu, who will give an online speech. Professor Yang Ping. Professor Yang, are you ready? Okay, please share your screen. Okay, let's start.
Okay, can you hear me?
Yes, sure.
Okay. Hello, everyone. It's a pleasure to give this talk. I briefly introduce our recent research related to the ISAC. First, thanks for the organizer, especially thanks for the chairs, Professor Yu and Professor Wu. The outline about our work contains, first I will introduce the background, then I will give some introduce about the research related on different waveforms. For example, first is about the linear frequency modulation is used for classical use for radar area, and then OFDM. Moreover, I will introduce some new waveforms, such as our research related to the orthogonal chip division multiplex, OCDM, and the AFDM, FN frequency division multiplexing. Furthermore, because we have a project with Meitan company, it's related to the application of some waveform. For example, we consider the use the OFDM to do the position for the UAV. So I will introduce this part later. First, about the background, as we know, there are many application scenarios for the ISAC. For example, for the low altitude detection, for the Hammond machine interdetection, for healthcare, for the transportation. So there are many scenarios for the ISAC, but in different scenarios, the function or the requirement for the sensing, for the communication may be different. So the waveform design to satisfy different requirement needed to be considered. In this case, there are many research related works. For example, they consider different functions for the computation, for the security, for the energy, many related works. Our main research or our main contents is related to the multi-functional ISAC waveform design and the UAV position algorithms. And the first part is related to the ISAC waveform design, such as we consider the OFDM and the linear frequency modulation, OCDM, AFDM, OTFs, and many waveforms. And we have compared those waveforms, such as for the communication performance and the sensing performance. The second part is related to the multi-base station aided position, high resolution position, because we have a project related to this topic. we consider some classic method based on such a music expressed. Recently, we have considered the AI-aided position, such as we consider the RL framework to some complexity environment. And the first part is related to we consider the RF-based waveform design we have proposed for the MIMO systems. We have proposed some new design schemes. For example, we can consider the MIMO and the index modulation. We consider the novel bit to symbol mapping rule. We have some result and detailed in this paper. We have analysis such as the basic transmitter, the communication receiver, and the radar receiver, and we detailed the expression such as the detector, such as the estimation for the parameters. Here we consider the such as the LMP-based method here. Also have some result for this research. From the result, we have found that our proposed method is better than the conventional case. Also, we have analysis such as the hit rate of the different method, and proposed method have a satisfied sensing performance. Also, we have analysis some bound for the waveform. For example, I consider the CRB bound for the proposed method. Moreover, we have focused on the off-dam based waveform because it's very classic for 5G. So we have considered the different variants for off-dam. For example, we consider the DFT as off-dam with index modulation, and another variants. We have compared the related performance, such as the energy, such as the PAPR and the BR, and also consider the sensing performance. Formulated the related mathematical models for those. So for example, we consider CISO case, and also we have considered the MIMO case for our proposed model. We also use the CS-based estimation method to the sensing. For the communication, we also consider some classic frequency domain equalizations to recover the signal. We have compared some performance metrics such as the PAPR performance, because we have consider some specificity of the subcarriers. So, for example, if we consider all of them with IMI, we can achieve better PAPR performance. Moreover, we also compare the BR performance for different schemes. Also, our proposed method can achieve a promising result. This is about the radar performance for different schemes. Because there are many other new waveforms have been proposed for ISAC, for example, OCDM. This method is dependent on use another transform, such as discrete Finel transform, and we also consider or research this topic. And this result have published in these papers. We have compared the OCDM and the off-dam. We have proposed a transmitter and the receiver, and we have compared the such as BR bound and the diversity, PAPR, and the impact of the carrier frequency offset on the proposed systems. we also have show the BR performance and the system performance for those scheme. From this figure, from the left figure, we can see that the proposed method can achieve better BR performance than conventional OFDM. The right part is about the system performance for different waveforms. You can see that they are very similar. Also, for another waveform, AFDM and frequency division multiplexing, because this waveform can use the similar structure, for example, similar to OFDM. Compared to OFDM, it have a two matrix relate to the phase, and use these two matrices, we can achieve the AFDM waveform. So this may be simple than the OCDM. But there have some issues for the AFDM. For example, it have been proved that AFDM can achieve full diversity under some conditions. For example, if the subcarrier is less than 5, and the diversity will be lost. So we have proposed some simple design or constellation optimization method to solve these problems. Moreover, because many waveforms have the orthogonal structures, so we have considered to use a unified framework for this. We have considered the OFDM, DFTS OFDM, and like this structure. To use a unified transfer chain framework for those systems, we have compared the PAPR, BR, and hit rate to this system. Another work is related to the multifunction of the ISAC system. Here we consider the different functions. For example, for function 1, we consider the PAPR reduction, and for function 2, we consider the completion of the error detection. For example, we consider the MDS maximum separate code with our proposed OFDM waveform. We have compared the BR performance, system performance, and PAPR performance, and this result is published in this paper. Moreover, we have considered such as use some deep learning-based method to the ISAC. In this instance, we have considered the mmWave application. For example, we considered the trajectory optimization, resource allocation for the ISAC. We have optimized the trajectory for the mmWave, and also we have considered the performance such as balancing the security rate and the system performance. Here the optimization algorithm. Here we consider to use the deep learning based method. For example, we consider use the PPO algorithm to solve this optimization problems. Moreover, we have a project with the midterm company, so the requirement of this project is related to propose some high resolution position method to the mmWave. So here we consider to combine the music expert and also multi-level weight method. And here we consider the different cases. For example, if the base station have different SRs, how to calculate the weight. width for different base station and achieve a more accurate result. Here we consider some classic methods such as based on the optimization. Moreover, for some complex case, for example, in some case, some link for some base station, the answer is not well. Here we consider the AI-based weight method. And those are the related publications to the above research. If you are interested in related topics, please refer in. Also, we have some result. For example, some research topics related to the topic, and also have some proposals to the MIT. There's also some open challenges and future research directions for this topic. For example, the fundamental trade-off limits, because there are different requirements on the performance metrics, especially for communication and sensing. So, how to make a promising trade-off based on different scenarios? This may be a question. Another is about the environment adaptation. So this is also a very important topic. For example, is for the transportation, for the healthcare. We may consider some dramatic environment. So the requirement may be different for other scenarios. Security also is a very important issues for the research. Moreover, combined with the AI, also AI native is also important research topic for this. In our research, we have considered some methods such as based on the RL method to the UAV optimization, but how to reduce the complexity, how to reuse the AI is also a very important issue. Also, there are some other gaps. And finally, there's an advancement because we have also organized some other topic or sessions or different conference. For example, we have a workshop for IEEE ICC. Also have some other special sessions for the International Conference on Signal Processing Systems. If you are interested for this topic, please share your contributions on this conference. So this all. Thanks.
Okay, thank you, Professor Yang, for a wonderful talk on the waveform design optimization. Okay, next will be given by the Liu Fan, who is the professor from Southeast University. Okay, let's welcome.
Okay, so thanks for this invitation, and I'm very honored to be here to introduce our most recent research. So today I will talk about sensing with random communication signals. Okay. And so here is the outline. I will first talk about the background challenges and some main results, and then summary of the talk. So here I will not elaborate on the background, and so there were very nice introduction by previous speakers. So I would like to start with the very classical problem, which is the waveform design for ISAC. We know that in ISAC systems we have three design methodologies. So sensing-centric means that we need to embed information in traditional radar waveforms, like we can embed information bits in chirp signals. So it has negligible impact on the sensing performance, but it will result in low spectral efficiency and incompatibility with current cellular networks. And then there's communication-centric, which is to sensing with standardized communication waveforms. So it is fully compatible with our current cellular networks, but it may lead to sensing performance degradation because it is not dedicatedly designed for sensing. And then there's joint design, which is to conceive novel waveforms based on nonlinear or non-convex optimization, and it can achieve a scalable sensing communication trade-off, but it can be very difficult to be implemented in the practical systems. Okay, so we can anticipate that in our future 6G networks, the communication-centric will be the primary design methodology for the ISAC waveform. So if we look at the communication-centric design, which is to use standardized communication waveform for sensing, then we'll have to look at the current, for example, the 5G advanced ISAC transmission. So basically, if you look at the 5G advanced frame structure, then you can see that 5G-A leverages the physical layer reference signal or chip signals for sensing, which occupy only 10 to 15% of the resources. This is very easy to be implemented, but far from optimal. Why is that? Because there are remaining 85% of the resources which are occupied by the data payload. Okay, so this is because we need to guarantee that the data payload is transmitted in a very high spectral efficiency and very high rate. So to improve the sensing performance, we have to exploit this data payload signal to improve the resolution and accuracy. Okay, so that is the main motivation, and that is also what we think that is significantly different from 5G advanced ISAC transmission to the 6G ISAC transmission. Okay. So just like introduced by Professor Carey in the first keynote, so there's a key challenge in the communication-centric ISAC transmission, which is a deterministic random trade-off in ISAC. So that is because if you look at the radar system, they typically employ well-designed deterministic signals with very good structure, very good correlation properties for target sensing, like phase-coded sequences with good ambiguity properties, or like chirp signals. But to convey information, the communication signal must be random. So that is perhaps the first lesson that we learned from information theory. For example, theoretically we can use Gaussian signals, which achieves the capacity of Gaussian channel, or we can use, in the practical system, we use constellation like QUAM and PSK. So if we do sensing using these random signals, then there will be performance degradation. Then there are two scientific problems here. One is how to characterize the sensing performance of a communication signal, not just a generic random signal, but a communication signal with specific structures. And then how to compensate for the sensing performance loss incurred by the randomness. Okay, so these are two problems that we need to deal with. Then let's look at what we did to solve these two problems. So to look at these issues, we should first define the structure of a communication signal. So what is a communication signal? What kind of structure does it have? So perhaps this is what we have learned in our university in the textbook, that this is a simplistic communication system that we have input random bit streams, right? So with that random bit stream, we should first do constellation mapping. So then we map these streams to the constellation S. So this S, there are constellation symbols. They are randomly drawn from a constellation codebook. Then with these symbols, we need to do a modulation. So the modulation is nothing but an orthogonal matrix or a unitary matrix here. So we just modulate all these symbols on some orthonormal basis. And then with that, we should, after that, we should do pulse shaping, because now after modulation, it is still a discrete signal, and we need to, convert it into a continuous baseband signal. So that is done by the pulse shaping. And pulse shaping is also to deal with the, to limit the bandwidth of a signal, and also to remove the intersymbol interference, okay? So here are some simple, examples of these 3 blocks. So for the constellation, we will generally look at Quorum and PSK, and they are both rotationally symmetric constellation. They satisfy these constraints. For example, they have 0 mean, 0 pseudo variance, and a unit variance, and all these symbols are IID drawn from the constellation codebook. And for the modulation basis, we have multiple examples. So for example, if this unitary matrix is an identity matrix, then this is nothing but a single carrier, because we transmit these symbols consecutively over the time domain. And if this is an IDFT matrix, we know it is OFDM, which is the default waveform that we are currently using in 4G and 5G. And if it is, for example, Hadamard matrix, we know that is CDMA 2000. And if it is a Kronecker product between IDFT and identity matrix, then it is OTFS. And also there's this AFDM, which has been mentioned by the previous speaker, which is also a unitary matrix. It is, we multiply 2 diagonal matrices at the left and right side of the IDFT. Then this is to use the chirp modulation basis, orthogonal chirp signals, to convert symbols. So these are modulation bases. They are all unitary matrices. And then there's Nyquist pulse shaping. So Nyquist pulse shaping, this is something that we learned from our communication theory textbook, that we need this pulse to have 0 intersymbol interference. It means that it will be, so if we sample this correlation of the pulse at the integer multiple of the symbol duration, then it should be 1 when n is 0, and if n is not 0, it must be 0. So that is the essentially Nyquist condition of the pulse shaping. Okay, so these are very generic conditions, and we would like to know that what kind of impact would these building blocks have on our sensing performance rather than the communication performance, okay? So our sensing metric is autocorrelation function. We're looking at ranging. So we're doing distance estimation for multiple targets. And the ACF is nothing but the self-correlation convolution of the signal XT. So here XT is this baseband signal that we just defined, okay? And so it has, so its geometry will reflect many, sensing related properties. For example, its main lobe width is the range resolution, okay? And its side lobe level will determine the multi-target detectability. So if you have a very high side lobe, then this high side lobe will mask the weak targets, okay? So we'll need to reduce the side lobe level of this autocorrelation function. And it is also related to our signal processing using matched filtering to do multi-target ranging. And also, we will also need to look at the ACF of random signals. So here, this is, if we look at random signals, then we cannot only measure its ACF using a single realization. We have to look at its statistical properties. So here, we look at its the square, the expectation of this square. So we impose a square because we need to measure its side lobe. And the expectation is because it is a random function. So we impose a random expectation on this square. And also we need to look at the coherent integration. So coherent integration is a traditional technique in radar system that we transmit multiple signals which are IID. And then we collect their reflected echoes and we do matched filtering. And then we simply add all these matched filtered outputs together and calculate the average. Then this kind of operation may effectively reduce the setup level generated by the random data, because with multiple coherent integration, you can reduce the randomness, you can reduce the variance, okay? But still, it is a random function. We have to look at the details. So what we have done is that we derive the closed form of this expectation for any, so for arbitrary modulation, arbitrary constellation, arbitrary pulse shaping. So for generic communication signal, its expectation of its squared ACF would have this kind of structure, which we call an iceberg in the sea structure. So what is that? So basically, you will see this is the results that for random signal, for random communication signal modulated by OFDM and QAM, 16 QAM symbols. So this blue line is this is autocorrelation function, the expectation of this autocorrelation function square. And if we do coherent integration, for example, 100 coherent integration, we can reduce this, blue line side lobe to the orange line. And if we further improve to 1000 integration, then we can reduce to 30 dB. So this kind of side lobe, they're generated by the random data. So this is the so-called sea level. And what is the iceberg? So the iceberg is this black line. So the iceberg part represents the squared mean of the autocorrelation function, which is purely determined by the pulse shaping. Okay? So imagine that you only transmit a deterministic pulse, then you will end up with this kind of ACF. But if you have random data on that, then this random data will generate some kind, what we call a sea level here, okay? So then that will increase your setup level. But by coherently integrating the measure filtering outputs, you can reduce this sea level part, okay? And this sea level part is actually the variance of the ACF. Okay, and now with this equation, we have all the building blocks here. We have the modulation basis, we have the constellation, we have the pulse shaping, we have the number of coherent integration. So this is a universal equation, and with that we need to figure out what kind of modulation, what kind of constellation and the pulse shaping is optimal for sensing, okay? So now the first problem is optimal modulation basis, so which is determined by this V matrix, and with different modulation bases, you have different V matrix here. And we managed to prove that under QAM and PSK constellation, this CP-OFDM, so OFDM with cyclic prefix, achieves the lowest average ranging side lobe level everywhere. So this is a comparison between 5 modulation bases. You have single carrier, you have OFDM, CDMA, OTFS, AFDM. So you can see OFDM is always has the lowest side lobe everywhere. And if you look at the concrete ranging performance, it is also significantly superior to other modulation type. So this is a modulation basis. And then what about the pulse shaping? So the pulse shaping, which lies here, it determines the iceberg structure. So what we did is that we tried to design this pulse while satisfying the Nyquist criterion. So we minimized the side lobe level within a specified region of interest. For example, here, if we're interested in detecting the targets within this small region, then we can simply minimize the side lobe in this region, just like to dig a hole in the iceberg, right? And then we end up with very good performance if we use this kind of pulse shaping to detect the targets within this, region. And then the constellation design. So here we employ the probabilistic constellation shaping, which is a classical technique that has been extensively used in current wireless communication system. And what we are concerned about is this fourth moment of the constellation, which is this kappa. So the fourth moment is the expectation of the fourth power of the constellation. And you can see that if we reduce the fourth moment of the constellation, we can reduce the set lobe of the ACF, right? So then in that case, we will also need to guarantee the communication throughput. So here we formulate a PCS problem, the probabilistic constellation shaping problem, to maximize the mutual information while we control the fourth moment of the constellation. And this kind of problem is a functional optimization problem and can be solved by a classical algorithm called the Blachau-Arimoto algorithm in information theory. And then you can see with that, we can end up with different type of constellation. So this is a 16 quorum and a 64 quorum, and with different probabilities. So the color on these constellations represent the transmission probability of different points. And then with that, by this kind of design, we can end up with a scalable performance trade-off between sensing and communication by this constellation design, okay? Okay, so finally a summary. So what we have done is we propose a framework to analyze sensing performance with random communication signals and to deal with the key challenge of deterministic random trade-off in ISAC system. And there are two key problems here. And here are our main results. We characterize the expected setup level for arbitrary communication signaling with the iceberg in the C structure. And we prove that OFDM is the optimal modulation basis for QUOM and PSK for ranging. And we propose the iceberg shaping technique to do pulse shaping, and we propose post-probabilistic constellation shaping to balance the sensing and communication performance trade-off. So future work may include the fundamental limits for multi-point and multi-band ISAC transmission, because now we are still looking at point-to-point transmission. And also we should look at ISAC signaling design for non-IID constellation, non-orthogonal waveform, and nonlinear modulation. And then finally, we may look at ISAC transmission design towards low-altitude wireless networks. Okay, so thanks for listening.
Thank you, Professor Liu. Thank you for bringing us to see the iceberg below the sea. Okay, let's welcome the next speaker, Mrs. Chen Lan from the DOCOMO Beijing Labs. It's our old friend. She will bring us a wonderful talk. Let's welcome.
为了节省时间啊，请允许我。
In order to save time, please allow me to share with you the PowerPoint in Chinese. Good morning, everyone. This is Chen Lan from DOCOMO Beijing Labs. I'm very glad today that I could be sharing with you the works that we've been doing on 6G ISAC and also the latest progress of DOCOMO. First of all, the ISAC value to 6G, everyone has already mentioned the value already. Simply just would like to summarize the three following things. The first one is that we've been having new sensing services and businesses. And second, we can have sensing-aided communication. Third of all, we can have sensing for AI. For instance, the sensing data as input of AI training and realize the value as well. In a cellular network, so while we're introducing the wireless sensing, I believe that this is very significant for us to realize the digital twin for 6G. We believe that while we have actually the different frequency bands from low frequency to high frequency, while protecting the privacy data of the users, we're able to collect the data massively. Also, with nationwide base stations and infrastructure, the cellular network support the large-scale information gatherings and also the cloud storage, and AI is going to be analysis and decision-making, and finally feedback to the physical world. The use cases of ISAC for 6G, we have two major categories, the preliminary and advanced. Preliminary use cases are there for the purpose to solve some commercial issues. For instance, the UAV detection and tracking. In the future, for the advanced use cases, we might have environmental reconstruction and also the realization of digital twins. For the primary use cases, without changing the existing commercial structure, it could be realized. But for the advanced use cases, because they require higher precisionists, that means that we need to also have certain amendments on the existing standards. So now you can see that the frequency band for sensing, it is influencing a lot. Here we have the 6G, sub-6G, and mmWave, and we have different parameter analysis on the influence to precisioners. mmWave has a higher bandwidth and shorter and narrower band. It could actually help us to have a very high precision sensing. So for mmWave, it is very much appealing in the advanced use cases. So the standardization for ISAC in 3GPP organization, everybody knows about this. I have simply concluded the progress in the ISAC and RAN. Especially, I want to say that while confronting with the 6G on 1.1 working group, we have already been proposing the standardization and research. In June, I think this is about to be finished. And when that's finished, it will be of great help to evaluate the potential technologies and also conduct deeper researches upon that. Before introducing the key technologies for ISAC, let me give you a sharing about the general principles behind the design. We believe that for communication and sensing, we could actually have on top of the core algorithm, we're able to promote the development of the researches, the waveform, the reference signal, resource multiplexing, multiple antenna, and reuse of the resources. Also, further, we are able to extend that to some of the sensing-related technologies, and also we can have communication for sensing technologies developed. Due to a limit of time, I'm just trying to share with you 3 cases of our advancements. The first one is unified waveform design. You all know that for the waveform design, it is extremely important and the basis. So traditionally, it is an OFDM-based communication system versus the sensing system that is based on chirp wave. They had different design of transmitter system. The challenge is that how do we actually use single transmitter structure to realize sensing and communication at the same time? Our proposal is OFDM should be in the core, and before IFT, we will introduce this module of the particular horizontal frequency domain processing module, and that we're able to generate the chirp wave. And also the sensing range can be extended from 1.3 kilometers to 1.9 kilometers, increasing by almost 40%. Another key technology here is the co-prime reference signal design, because sensing is really something that cannot be done without the co-prime reference signal. In order to reduce the impact to the core system, we are thinking about reusing the existing signals as much as possible. For instance, we are taking the range in sensing, for instance. We could take a look and reference of those band-like signal, but the problem is that how that we are able to eliminate the problem of ambiguity of the long distance. So that means that we need to introduce such a kind of intertwining tree structure to solve this problem. But the problem is that the upfront investment is very high. So how do we actually make sure that we could reduce the overall consumption as soon as possible and as much as possible? Also here, what we consider is that we use 2 similar size signals to actually generate the different cycles so that the ambiguity could be resolved. And also on the bottom right, what you're able to see here is that while with a similar fidelity and precision compared with the traditional method, this new method is going to actually reduce the consumption from 43% to 14%.
And the third part of the work is for the digital twin environment reconstruction. So if we just use the base station equipment, since they are in fixed positions and they are affected by the arena size, normally the resolution is not that high. So how do we use the portable devices to do UE assisted environment sensing. So our design mindset is that we refer to the synthetic aperture of radar. So we can do the movement of the testing device when it's moving to a certain scale. And then we can collect the echo of the users, and we use the advanced algorithm to realize very accurate reconstruction of the environment. So on the bottom right, if we use 3.5 giga at 100 megahertz, we can realize meter level of city reconstruction. So then the two pieces of work from our headquarters. So 6G is not only available for communication. A lot of things are beyond the communication. So for 6G systems design and the optimization normally would be very complex. So how do we achieve low price and high efficiency? We think that the network digital twin is a new mindset or new plan. So we have two pieces of work. One is 6G emulator, and the other is the digital experiment. So for the emulator or simulator, we use LiDAR and camera to have the point cloud collected, and then through the 3D polygon data, we would generate the emulation or simulation channel. And then for the propagation channel and the simulation channel, we can have the digital twin simulators. Then at any point, we can get the throughput of the user in real time and also other experience parameters. And this is a very short demo. You can take a look. So this is the reconstructed point cloud plus the normal signal channel environment data. Here are the multiple users in the environment, and the rate can be tested in real time. So user 2 just went from left to right, and since the environment went from in-loss to loss, so you can see the real-time throughput improvement. And the second part of the work is a cooperation project with Ericsson, a digital trial. So in the middle, you see the digitally reconstructed city in Sweden, and the digital avatar can move in the street, and we can choose the best waveform, and the throughput can be calculated in real time. And in this trial, there is the only base station processing equipment that is using the experimental equipment. Then for the other environment and other elements, they are all realized through digital twin. And the two experiments are pretty initial stage. In the future, we will use the air interface key technologies to improve the performance to really have the dynamic reconstruction of the environment. So for our center, we will cooperate with the colleagues to speed up the innovation and co-build a beautiful 6G future with higher value. Thank you.
Thank you for Professor Chen. Thank you for a wonderful talk. So next talk was given by Jin Jing from the China Mobile Research Institute. Okay, let's welcome.
Distinguished leaders and guests, good morning. So I will just use Chinese then. So very happy to be here and share a bit about the ISAC and our progress. So we will talk about the use case, and we will talk about the high accuracy cooperative ISAC. And here are some of the use cases. In the 5G network, we already did some ISAC experiments, for example, in low altitude and on the water. We have done some validations, but we found that especially based on 5G-A, with the current network, the situation is not that good. We do have a lot of noise, and also the carrier frequency is pretty low. So we do have the function of like intrusion testing, but the fidelity is not that good. So in the future, how do we improve the performance? Since we know that the beginning of ISAC is that we think about how we integrate the radar capability into the communication network. And it is good because it's ubiquitous and it's a massive scale. So can we improve the scale so that we can lower the cost? And we found that if we do the single base station sensing, the capability is pretty limited. And also there is the requirement of cost. So in the future, can we use like cooperative sensing? So like we have the node A and B and C, so that we can have the cooperative sensing capability established. And then I think in order to get lower cost, we could do this. And after the low cost initiative, can we improve the accuracy? And that is another issue that we're thinking of. So in the early phase, we were looking at the potential cooperative ISAC, and there are several challenges. For example, when we face the low altitude, the traditional base stations would have users on the ground. But if we go to the low altitude, we need to think about the vertical coverage. And since Echo has the two-stage of channels of modeling, and the loss is pretty big, so how we improve or increase the coverage, that is another challenge. And we do have some solutions already tested in the current network. Some other speakers talked about the radar wave, and some say that we can improve based on hardware. And the other thing is about the sensing accuracy, because single node is very limited in its capability. Especially if we can have the cooperative sensing of A out and B in, then we need to do accurate synchronization to really improve the ISAC capabilities. And if we want to have more nodes in the cooperation, then we need to think about how we merge the data of multiple nodes. And that is another direction that we're thinking about. And the third is about the reliability. Sometimes it's affected because sometimes the environment is bad. In the simulation, we may say, yeah, the accuracy is good, it's a centimeter level. But when we test it in real world, there is a lot of non-ideal situation that can affect us. The other challenge is that if we do networking at scale, sometimes we can have serious interference, especially the signal sent by the base station. Normally it's high power. So in the networking environment, interference is pretty serious. So for the first and third and fourth, actually we'd already tried in the testing or in our existing network. But today, I think we want to talk about the improvement of the accuracy. So in terms of the accuracy estimation, we may have the joint estimation, but we found that, yeah, okay, the performance seems good, but the definition of resolution is not really catching up. So we also did some research there. So for the traditional resolution, it means that we do it with one dimension, for example, distance. It's related to the bandwidth. But then if it's velocity dimension, then of course it's related to the time of observation. And the angle, of course, is related to the aperture. And then for the sensing accuracy, it's basically this formula. It's related to both resolution and SNR. So at a certain resolution, the better the SNR, the better the accuracy. And we found that if it's just single dimension, maybe we have two targets, that we cannot distinguish. From the distance or from the angle perspective, we cannot separate the two. But if we do the estimation, sometimes we can join the two signals together. Then it's estimatable and it's tellable. Then we have this system resolution concept. So if we combine the resolution in different dimensions, like on the left, they are two dimensions, like distance and angle, both untellable. But if we get a new equation, if we consider them both comprehensively, then we can operate on that. So there are some of the simulation verifications. So on the left side, that's a single dimensional case, we wanted to test the theory to see whether it's correct. And then we did the backwards inference, and we think that it's matching. And on the right side, this is multidimensional, like multiple distance or angle or velocity or distance. So you see that outside of the red line, it's all distinguishable. In the past, it was just within the black box. So then we thought maybe we can use different nodes and different multiple base stations to do this. And we thought that, yeah, we can look at the lack of accuracy from three perspectives. First is the accuracy of the speed. So if we just measure the speed, well, the radial velocity is good, but when we test not the velocity of the radial, then it's very difficult. And we have the Doppler blind spot issue. So if it's 1 point, then of course it's two variants. So we need not just one equation, but two equations. So we have maybe two stations to look at it. But for multiple stations, for each we have a radial speed and a velocity, and then we have also the tangential speed. And the second thing is that we found that for the tangential velocity, well, the biggest influence is the taking off and the landing of the UAV, because it's vertical. But for the radial, normally it's 0, right? But for the vertical, it's a tangential velocity, so it's really hard to get. So we thought maybe we can deploy some of the planes to help us do the ultra low altitude UAV sensing. And the second thing is, yeah, maybe we can improve the velocity measurement, but the overhead is still too big. So other speakers mentioned about time-wise or frequency-wise, you need the overhead to do the sensing. So we did some initial calculation. The maximum speed, non-blurry speed, is related to the resolution. So we have the requirement on the speed and also the velocity and the resolution. So the symbol requirement is pretty high. And what we want to do is, can we do a double cycle setting? So that means in the first cycle, it's a pretty dense scattering, and in the second phase, it's pretty scattered or sparse. So then we can get the highest unambiguous velocity guaranteed. Then in the second phase, we can prolong that, so the overall observation time is good. So the resolution will be okay. And after the simulation, we found that the estimated result, compared to the last slide, actually it was pretty close. But the overhead is actually much lower, from 120 to 12 to 15 signals, so basically 80% of reduction. So the industry discussed about this. It's not just about the double cycle, a double period of the speed as well as the distance. So maybe in the first period we use part of the bandwidth, but in the second period we can use all the bandwidth. So that is something we can do for the non-even signal setting. The second is about the angular velocity inaccuracy, because for a lot of base stations normally it's not 1 to 1, and for a lot of arrays we would share one channel. So then the interval of channel is getting bigger, and then we can have some ambiguity of the angles, and there could be a lot of virtual angles involved. So in radar, there's also the issue like this, and it's pretty commonly seen. And we thought that, okay, we can just add a bit more nodes so that the overlap, the intersection will be clearer. We can get from 1 point or 2 point or multiple points, then we can know the position. And this is a simple way. If I send from A to B, then B feeds back to A, then we can find the intersection, and according to the distance and the latency, we can get the intersection of and also the distance, and we can solve the shadow issue. And since it's in and out twice, and the time overhead is pretty high, so we thought maybe we can use the sum difference beam to do this, because we don't need to seek the peak, so we can avoid the shadow. And the other thing is that we can do the enhanced alignment. So in the past, we would choose the 2 best beams and we would do the algorithm, but then we found that it's not the optimal. We chose the best first beam, the top 1 beam, and the estimated result would be more accurate, and the angle is smaller. Now we can see the gain is very good, 5 dB. And this is the thought on the angular. And then the third is about the distance accuracy. So we use the multi-node sensing. And to comprehensively think about this, we have multiple nodes, and in the last step we did the estimation and also the angle measurement and velocity measurement. So how do we incorporate or integrate the data? Actually, the industry is trying a lot of things. You see, the first step is the signal level fusion. So the raw data can all be accessed. Then the transmission cost overhead is pretty high, so it can pose some pressure on the network. Second, maybe we can do a certain level of processing. For example, if we get some characteristics, then we can pass on the characteristics. This is the symbol level fusion with lower overhead, and we can use maybe AI to make it more accurate. Then the data level fusion. So after processing a bit of the volume, then we can then upload, and then the overhead is the smallest. So currently we're thinking about the first two, the symbol level fusion. We did some analysis in the multi-node collaboration. Apart from that, we also have the synchronization errors and so on. So for this part of the work, it's about the symbol level fusion and also the error, and we consider them together. If we have multiple nodes and look at the error and multi-target data fusion, compared to the single node, the gain is twice as much. And then we tried, because the overhead is big, and we tried to see how we would do when we do the symbol level. So we had some algorithms proposed. The intermediary values or characteristic values uploaded, and then in the server we can get converged, and then we can also improve by once compared to the single node. And we also derived from that. Just now the result says that we can have multiple base stations, but we think that compared to the ground target or a close-by target, I think the loss is pretty big. So we had some combined deployment from micro and macro. And also, for example, the smart robots and smart terminals can do this, and they will be closer to the target. And performance-wise, the accuracy is also improved, like by 70%. And we are also trying to combine with AI better, because AI is very good at dealing with the data fusion. So AI proposed the distributed way. So at each node, they will calculate and then send it back. So the signal level of data is merged to the multi-node processing function. So we have the multi-node fusion or AI method. So we can do parameter-based and then we would train the angle and distance and identify them together. And you can see some of the results. On the left, stage 1 to 3, we got from one station, and then the 2 stations together or 3 stations together, and we can see that if we add it up, there is a big improvement in the performance. And on the right side, you can see that if we compare it to multi-node without AI, or compared to the traditional multi-node data fusion, we can further reduce the error by like around 10%. So it's definitely better than non-AI approach. We can get some time gain.
And last but not least, we could see that originally we wanted to have some supplementation from a theory standpoint, and also wanted to have a very good combination with the system resolution. But still, at the same time, on top of dual base station sensing, we want to have multi-nodes added to it in order to improve the precision as a whole. Hopefully that we are able to be empowered by artificial intelligence, which is quite almighty, so that we are able to improve the sensing and communication capability in terms of the target identification and detection, and some of the other capabilities. And now you know that ISAC is a very hot topic, so we really hope that we are able to do a lot of work all together with you, so that we are able to promote the ISAC into commercial use and also closed loop. Thank you. Thanks a lot for this wonderful presentation about the topic. Now let's have Xiaomi, Zhang Zhenyu from Xiaomi.
Bothering.
尊敬的各位领导、各位专家，大家上午好，我是来自。
Hello everyone, this is from Xiaomi Standardized Working Group, 3GPP team of Xiaomi. My name is 3GPP. Very glad to share with you some of the works that we've been doing. Today, what I'm talking about is the ISAC channel modeling towards the 3GPP. First of all, this is a very critical technology here. And before 3GPP, normally speaking, we conducted the channel modeling like 5G 911 and ISAC for the 5G at the later stage. And at early as 2001, we actually proposed the ISAC modeling towards 3GPP standardization in China. Also in 2023, October, we successfully set this up as a project, and also Professor Li Yangyang, as an expert, was the reporter. Before the start of my presentation, I would like to extend my gratitude to Zhang Jianhua, because together with the PTSU and Beijing Jiao Tong University, we've been doing a lot on the works of the channel verification and testing. So everyone has very good marks left to 3GPP. On this particular slide, we're talking about those basic frameworks of the discussion in 3GPP. Today I'm going to talk about several things. First one is the target channel, including single mode, single point, multiple mode, and RCS. And second one is about the target channel. You know that we have the different size of it, constellation modeling, the large and small scale fading, Doppler, and also EO type 2 modeling. Next one is the background channel, which consider the standardization for the reference signal. The first one is the general modeling, be it it's a single or dual station. For the headset and base station and target are going to be everything. Also in 3GPP, we're considering 4 targets: the vehicle, human, UAV, and AGV in the factory. So for those non-interested targets, we call it the EO, environment object. And there are actually several types. The first one is that EO with the small size, which is type 1. Second is like the large size wall and ground, which is EO type 2. On the right-hand side, actually, for all the kind of channels, we are able to divide it into 2 categories. The first one is that we have 3 targets in the middle. This channel is called the target channel. So by having the random scattering cluster, and to have this scattering and reflection. Another thing is not through this particular middle part. We call it the background target, and we're going to be reflecting to the 3G receiver. So for this part, this is about the target modeling. In the very beginning, what we're considering the particular target, we use single point in order to know the positioning. But if you want to do more details, you need to have multiple points. So this is something that we conducted together with Professor Zhang. What I want to say is that on PVP, you're able to see that there are actually multiple peaks in 3D PP, and also we make the human model into single point and multiple points and single point for vehicle. This slide is about the modeling for target for polarization matrix, and we have actually this polarization matrix of target to describe that when there is an electric wave gaining through, what is the changes on the phase. So the phase change is pretty random, but for XPR, the photo on the right demonstrates that there is actually a kind of leak of the power, and we have some conducting the analysis and testing and finding out that the distribution feature and everything is the result after the real testing. And this particular slide is most important thing, which is the general RCS modeling. We have dual versus single station. And in the single station monostatic, we have actually several parts. The first one is RSA of A, which is large scale, and then B1 and B2, which are actually the parameters for small scale. For models, we have single and also dual. And also that we have different models, and the major difference is that on B1 value. So this is actually describe a directional pattern function. For the biostatic sensing, we may have actually two ways. First of all, we may we may take reference of the formula. And also on the vehicle itself, we might actually have some mirror reflection, or there might be actually a surrounding scattering, and there might be having a forward scattering peak generated. This is a model regarding humankind. You can see that for the monostatic RSA, actually we call that this is a full spectrum. But for the biostatic stage RSA, we are in favor of the directional modeling. So we have also very good peak map here on the right, which is the RCS change on the human body surface when it reached 0 degrees Celsius. And also we have been conducting testing in real time. For instance, we are scanning these parameters and making this input to the platform to do emulation. For the vehicle itself, on the front, back, and left, right, there is actually a very clear power on the top, so we have to make it into a peak value. Also, while the angles are changing, the peak rate is reducing, so we just reuse this radial pattern of 3GPP function to describe this change. Also, for the A, which is the mean value, we are going to do a very good work on this function. And also B2 is a log normal distribution with the stat of 5.91 dB. This slide talks about the UAV. We have been having two kinds, small versus big. For the large-scale UAV, this is the job and work that we've been conducting with Professor Zhang. The pattern on the right, which is quite directional, is different from vehicle, right? UAV is in the sky. So for the top and bottom, front, back, left, and right, we have multiple points. Those parameters are something after the calculation of the real situation. The next one is about the target channel modeling. In the 3GPP discussions, we've been considering 4 scenarios. First is that line of sight to, and also from the human to vehicle, human to headset, vehicle to headset, and vehicle to human. Actually, you can see that here is a direct path versus indirect path. Also, for the target channel modeling, the major important thing is a cascading method. The bottom left here, actually, we are having a cascading of 2 channels. But if this is a cascaded connection, if you want to calculate the channel matrix, and then to do convolution, etc., this might be something quite disadvantageous. And also, if there's a single container, this is going to be having loss instead of gain. So what we consider is that on 2 sides, we may have a small-scale model to establish the parameters, and then conducting this cascading connection to generate the end-to-end figures before having the channel model. And also, the second photo is quite simplified, non-cascaded, connection of model, and we just put this current sensing capability into the channel of 6G. But still, for the rate level full coupling, we also consider far left and right. And also, we actually believe that the bottom two things are very important. If there are 10 roots on the top and on the left, we are able to do matching one by one. So we can actually make a match of any of the on the left to any of the right. And here we are talking about the large-scale path loss model. Considering the two sides of the online modeling, a very easy way is that we just add the path loss on each other. But here that means that there is a additional repetitive calculation and some of the missed calculation. So this is a testing that we've been conducting in the teaching lab of Professor Zhang to validate the availability. And now this is the dual methods of target channel modeling. So from base station to target object, and from target object to the receiving side. So we are actually generating the angle according to positioning and polarization. Also, as for the mobility to the model, the Doppler, and finally we generate the channel coefficients of target versus non-target, and then came up with the channel matrix. This is the background channel modeling. Actually, it was not passing through the sensing object. And also in the bistatic sensing, it is quite simple and straightforward. But in terms of monostatic, now we don't have this particular model existed. We had discussions in 3GPP, but still on the way. The photo on the right is a very brief verification that we've been doing. So we hope that we can have a human being added as a objective or the target, and also to come up with this result. So against that scenario of BASTAC, we are able to mitigate the channel modeling. When we have everything ready, we may consider doing a combination. So in the sensing, we have to consider the absolute time delay to do positioning, and also we need to consider the kind of a power and normalization and target and background. So here, what I want to showcase is that science is not something quite fancy, but this is something that's servicing people. And in Xiaomi, we have multiple products. Also in 6G, we really hope that we do have new technologies, ISAC and AI, be it on the headsets and also breathing testing, or some of the ADAS used by the vehicles. We are able to bring new changes to people's lives. And also, I do hope that everyone can enjoy the benefits brought by the science and technology. This is the end of my presentation. Thank you. Thank you very much, the colleague from Xiaomi.
The next speaker from Wu Qingqing from Shanghai Jiao Tong University, who will give a talk on RS empowered 6G. 特别是他是带着发烧，今天早上发烧感冒，我们特别感谢。
And he's having big fever this morning, so very grateful to your effort. All right, thank you very much. Today, I am very honored to have the opportunity to give you a report about this topic, intelligent service empowered 6G integrated sensing and communication from coexistence to reciprocity. Today, this is my topic, right? So in the previous years, what we were doing were some key technology researches on communication, and recently we've been doing a lot of works on the sensing and also ISAC as well. This is an ISAC conference, so just skip here the reason why we have to research on ISAC and how to realize this. Actually, traditionally, for the intelligent reflective plane, it is a reflective equipment, and it can make it transparent. So that means that it is like a signal anchor. If you put this beside the base station, this is pretty much being regarded as a small radar. And also, if you actually position this near the base station, theoretically, it is having the same method when we're using the radar sensing. Here, what we are introducing is that we're using that in the space, and also we are taking more aggressive ways to put into the surface of the vehicle. Also, we had multiple discussions and proposals by some of the companies in this industry that how they are able to embed this into this so that we are able to have some dedicated design for vehicles. In the space, I believe that first of all, it could be regarded as a signal anchor. In a smart factory or in a big conference hall, when we have this intelligent super surface, for robots and for some of the objects, we may have a better sensing capability. Also, except for deploying this in the space, but also we may designate the deployment upon certain objects. Say for new energy vehicle, it is having a lot of scientific know-hows, so we can actually improve the ISAC performance, and also the cellular-based UAV of ISAC. If I want to identify and detect that UAV, if there's an intelligent surface, we are able to also increase our precision of sensing. And very last one is what we call a hybrid RS, because we could make it into totally resolution, but under certain condition, when we have certain sensors, itself can become a processor of signals, so that it could be collaborated and coordinated with the base station further, and to enlarge the scope of sensing. These are the basic, structures that we talk about. And as for the role to the integrated sensing, there are several parts. The first one is the regulation capability of the channel. And normally speaking, you know that the ISAC is adjusting and regulate the channel. But actually, as for communication and sensing, essentially there are actually two different business types, but they do have something quite similar. For instance, I may actually have a detection under certain circumstances, and I want to have more response wave. And that, I believe, is quite relevant to the demands and needs of communication. But sometimes we may have different demands. Sometimes when I'm sending signal, I do not care about the information itself in sensing, but in communication we pay attention to the nature of the information because there are interference. So between sensing and communication, there are actually differences and commonalities. So the intelligent surface is playing a very important role. How that we are able to make a trade-off between different points. And the very first point, as I already mentioned, is the reflection of the channel. For instance, for the multi-target sensing, what I wish to do is that we are able to reduce the channel correlation so that I can be more laser focused. But for communication, especially the high-speed communication, I want to have the multiple stream transmission. So what I want to realize is that the kind of a RAN can be further increased and improved for the channel. So there is a big difference. Also, the RIS is actually a device that can be deployed. But for deployment, I could have distributed versus centralized. And from an energy standpoint, if you want to sense the target, for the centralized deployment can help us to increase the energy of the echo. But if there are many different task types, say positioning, estimation, and parameter estimation of that object, if I have the distributed method as chosen, this might help to reduce the energy that will be recovered, but it is providing more freedom of level to the approximate analysis. And I may have different anchors, and different anchors are able to help us to observe the object. So this is a multi-dimensional sensing. Here, we are talking about the reciprocity between sensing and communication. For instance, for sensing, we could actually sense the information and aid the communication. Also, at the same time, there might be a communication-assisted sensing. The communication signal can be the source of the sensing, and at the end of the day, it is pretty much about the coordination between sensing and communication. Let me give you a report about the recent works. First one, in terms of IS4 sensing, the first one and the most simple one. Traditionally, the base station, if they want to sense, they just sense signal at a certain direction. If you get the echo, and you're going to detect that object existence. This is pretty much based on the line of sight. But if this is a non-line of sight, it's very complicated. So you can see that there is no line of sight path, but by having this RS, I can set up a dedicated path to the object. Also, for the intelligent surface, the relevant kind of positioning could be deeply deployed in the past because the itself is a hardware. So if we are able to detect that on that certain direction there is an object, and then by having geometry relations, we're able to finally calculate the final result. The major contribution of this work is that traditionally we had the 3-degree transmitting of the satellite and also getting back the signal and getting echoes. But if you're coming back to the base station to process, essentially, there might be a problem about the bird angle. Be it it's target 1 or 2, you actually had the very first result, and also to get a feedback. How do we solve this issue? We have been borrowing what we called the signal labeling. That means that when we are sending signal from the base station, we will designate, say, channel 1 is for that particular direction, 30 degree against the RRS, and also 60 degree as well. That is going to be the way for us to detect the echo strength, and also we are able to have a very precision and precise notification, and also sensing of that user within certain kilometers. And also some level, I think that it is going to be very helpful to us. So just now we talk about the RS, but if we have the multiple RS, we are able to have a much better performance increase. So it could be deployed more often in the space. What we do is that we have multiple RS to actually help us to deal with the difficulties. Here, the biggest difference is that in terms of low latency and also estimation, normally speaking, I use 2 IRS to realize this particular sensing and also positioning. Also from the super service 1 to 2 and all the way to 2 and also back off. Here we've got 2 balls, and also from the RS1 to the sensing target and to RS2. Also, here is a eclipse, and also when you have actually limitations, I think that this particular oval shape of the ball is able to help us to understand the target, and also we can realize the sensing through algorithms as well. If you're comparing this with the others, you can take a look at the details later on. Just now, we have mentioned something that TAV related sensing and also estimate on the distance, and also apart from that, another very important thing is that if we don't have angle information, we can have more precise positioning. So if you had this estimation of time, and also I believe that you are able to realize this particular target more often, and also precision could be improved by doing so. So here we've been having some methodologies proposed, and at the end of the day, it is about the 3-stage location estimation and algorithm. So for instance, for the comparing with only 1 RS used, we can reduce the CRB, and if you're comparing the parameters of latency and also the angle, we have also better result. And also at the same time, we are able to realize a lower MSE for the different popular algorithms. Just now, we already said that this is going to be a very potential way for us to demonstrate. For instance, in the V2X, in the future, we might have iOS on top of every vehicle. Normally speaking, they're using metals, and this is going to particularly reflect. Also, by leveraging the RS in certain conditions, say onboard and car glass, etc., right? So this is going to be more laser focused. So at the same time, we could increase the positionings of the positioning from the road to the vehicle. And also next one is that how that we are going to coordinate between the RS and base station, how to make a connection, and also we want to actually reduce the CRB algorithm intensity. Actually, for each RS, we need to connect it with 2 to 3 and 2 to 4 base stations in order to make it quite performance. When you have 2 base stations get access to this, you're already having a very good result. And if it's above 4 point, and that means that almost all the precise positioning could be very accurate. And also here for ISAC, we already proposed the idea of sensing-assisted computation, and for the users, if they want to have communication, and also at the same time, if they want to have better sensing, that's why we have emphasized that for the first step, we have to make a combination. And second, when we have the sensing signal, as for the vehicle, we're going to provide the tracking capability so that there will be a higher efficient commute. And also from the price standpoint, because for the vehicles, we need to make it transparent and passing through, and also we have to have the reflections. So just because of the sensing stage, for those feeded or for the reflected energy, the more, the better for us to position that vehicle. But at the same time, on the contrary, the overall rate of communication is going to be lower. And also it's taking a certain proportion of the time. So the overall rate of transmission could be reduced. So we just design this 2 stages protocol and algorithms. Say, under which circumstances are we able to have a synergetic moment for all the players in 6G era. And also, we've been verifying some of our methods and comparing with the original algorithm while realizing the same rate, our power consumption and power generation could be much lower. And the next question is that in the telecommunication, you have a very different interference. As for sensing, I did not care about the detailed information of that message, right? I just only care that whether the signal is strong enough. So we just make the trash of not wanted resources as valuable things. So actually, sometimes when there's information from people 2 to person 1, it might be regarded as a different landing gear or different things. So when we're having sensing, as for the vehicle 2, it has a very good sensing signal. So based on this echo, got back from number 1 vehicle, and also it is going to be helping them to have a much better communication, because they've been having a very good sensing capability. So for what we do is that, for the communication interference, we are changing this into a comprehensive work. And here we have several stages. First stage is that we have a new sensing, and the sensing signals could be used for the first vehicle to communicate, and also at the same time it could be used on the vehicle 2. And the topology existed like this. So versus those non-agricultural sensing, we are able to compare and also having improvement.
And finally, just 1 minute to talk about our latest work, the movable intelligence service. Because the current service, we know that for the manufacturers, they're really emphasizing on the power consumption, right? We want it to be more low consumption. or semi-static. That means during work we don't need to change the phase. We spend a lot of energy on thinking about how we do this. So normally we need to change the phase, but if you want to track, of course you need to change the beam, and then you need to change the phase. And if you want to change the phase, you need to change each unit. Then there's the energy consumption, and there's the hardware cost. So if we have two static phase surface, then everything is just static. We don't need any phase control. Then for each surface, we can predefine and pre-optimize, so that with one hypersurface and the movement from another hypersurface, then we can realize the move. So it's just like closing the window with different folds. Like you move one thing and the pattern on the other thing also changes. So maybe we can have a small hypersurface moving on the surface of another hypersurface. Then the overlap is a new beam form. So when we actually implement, there are several different options, like two circles with the same radius, and when they rotate together, we can realize better scanning. We can realize multiple target sensing and multiple target communication, and we did relevant analysis. And finally, we also made this system on the 12.2 giga. We made the two hypersurface, and with the relevant movement, relative movement of the two, within a certain scope, for example, from -60 to 60 degrees, we can realize very good beam scanning. So basically, that is my presentation, and this is our reference. Thank you. Thank you, Professor Wu.
So next will be the panel discussion, so we do not have so much time, so let's save the time. Please, Yang was chair the next panel discussion. Okay? 请这边我们将有下面几位嘉宾有
We have the following guests. Jiang Zhen, Technical Director from China Telecom, and Fei Qin, President of Vivo Communication Research Institute, and Wang Guangjian, Huawei Senior Research Expert, and Feng Zhu, Dean of School of Information and Communication Engineering, Beijing University of Posts and Telecommunications. Thank you. And I want to thank everyone for staying till the last. So I guarantee that I won't interfere with your lunch. We will end at 12:30. So we heard about the topics on ISAC, and of course we felt a lot, and we had been inspired a lot, and a lot of things were mentioned about the opportunities and challenges from different angles. So the first question is pretty easy. So during Professor Zhang's presentation, he talked about smart home and UAV, and Chen Lan also talked about the important and future scenarios. So since the panelists on stage are from the industry, so what is the killer application for ISAC from your perspective? Do you agree with the previous speakers? Mr. Jiang, please. So I think Docomo and other experts, they shared about this. I think there are multiple scenarios and use cases, but low altitude is definitely a very fitting scenario. There are two things. One is that it is a very simple scenario, and it provides a very good time frame for ISAC to go from simple to complex. Then we can accumulate the experience. That's one thing. The other thing is to develop a technology, we need the market scale. For low altitude or for UAV, the market scale is enough. And for the equipment manufacturers, they could be interested in this because of the potential of the market. And right now, I think that's definitely promising. Then with the development of 6G, of course, there are more and more scenarios that can enable ISAC to have its value. Thank you. So, what about Mr. Qinfei? I want to answer from another perspective. For 6G ISAC, for ISAC killer application, I think we could try to answer on like what it can do when we achieve ISAC. Because from my understanding, sensing and communication, for this, there was radar technology. So I think this is the production of the combination of radar and the communication. So it's about testing for the distance, the speed, and the angle, and of course for the latency, and also that's one of the dimension. Then for the Doppler effect or for the latency, there's the second order function, which is the variant, the Doppler variation, and also the change of the latency. So that can have the micro Doppler effect or the relative kind of error. So that's the second part. So we can use that to maybe detect the trajectory or the breathing, or we can use the micro Doppler to see the frequency of the breathing, or we can see the frequency of the RPM of the UAV, or sometimes they use this to check the vibration of the wing of the locust king. Because the frequencies is different from the normal locust, so they want to guide the locust king to not go to the farm, but to other places. So there are a lot of things that can be done, but we need to have the subjective understanding. For communication system and its sensing is not professional radar. Objectively speaking, the operators, the advantage is that they have millions of base stations, maybe more than 10 million, covering all of the densely populated area with commercial activities, and the coverage is pretty good in those areas. So maybe we don't need that much accuracy or that reliable data when we sense, but it's always there 24/7, and also it's ubiquitous in time and in use cases. And the sensing result is low cost because you don't need professional radar. You just need the current signal, the current technology. With very low overhead, you can get the big data. And the ubiquitous, low cost big data can be used for the societal management or the UAV flying management. And of course, we cannot use it to avoid the obstacles. Still, UAV needs to rely on its own vision or sensing. But what we can do is that, if it's a forbidden zone for UAV, we can just keep it out, because on a level, the UAV management needs to rely on its own GPS and also some external rules. But some of the drones, the violators, the rare violators, would fly into the no-fly zone, and then we can detect that. So for management or regulation, or maybe we can manage the traffic or maybe the passenger flow on the ground. So, for example, at the entrance of the subway station, we know where to start a breakfast cart vendor business. So that is the value. And for example, you have a cell phone in your pocket. You can use your cell phone to search the signal, or it can detect your pulse or breathing or heartbeat. So with that kind of technology, the 1.4 billion Chinese population can have better life. For example, the day-to-day caregiving can be covered by the mobile device without a lot of cost. And when there's an issue, maybe just 1% or maybe 0.1% of people still need to buy the professional equipment. But for the mass, they just have another way to provide like day-to-day care. So I think the killer application of ISAC, it's hard to answer, but it's definitely very useful. Okay, thank you, Mr. Qing. And you mentioned something about the monitoring of the information, right? So let's just jump to how do we define or draw the line of user privacy. And Mr. Wang, I just want to give you some restraint. You cannot just answer like without any boundary. So today we have the OEM, we have the regulator, we have the operator. So to protect yourself against other people sensing, what is the boundary? And also for Europe, things are pretty conservative, but in China, can we reach consensus in this? For privacy, this is a hot topic in ISAC. So in the traditional sense, we say, yeah, ISAC would get some critical information, but if we look at the comprehensive result in the 5G ISAC, actually it's different from the optic system. So whether there is private information, it's related to a lot of use cases. So with that, for the boundary, do we put the privacy protection to layer 1 or layer 2 or 3? This is still being discussed. And maybe with different cases, we have different definition. But no matter what, the privacy, especially in the cellular system, the communication-based systems, we still hope that within a standardized system, we can define it and have a full set of privacy protection framework. And maybe from the testing of the sensing signal, then we can test and report and then compute. And maybe we can merge the privacy protection to the end-to-end communication system. And that is very necessary. Now for 3GPP, for R19 or R20, especially for positioning and for the sensing outside of positioning, people are talking about this in different work groups. And I believe things will converge. And that is for standard. The other thing is, if we want to have privacy protection, it's not just about the standard protocols like the measurement and reporting. We also need to think about it from the data perspective, see if there are newer encryption algorithms to protect us mathematically. For example, the same state encryption and other algorithms. Thank you. And I also have another question for Mr. Feng, because you are the expert of resource allocation and optimization. Just now, in the presentation by Professor Liu Fan, it was covered that how do we distribute the resource? 85% of the sensing, 15% for communication. So do you agree, or do you think that things are different in different use cases? Some are like sensing heavy, some are communication heavy. So what is your thought or suggestion? So just now, Professor Liu Fan talked about resource. For ISAC, I think I really love this topic. ISAC, or the merge of communication and sensing. And integration, it's actually deeper than just integration. So For the integration, it means that we use the communication system's resources to do sensing or detection. But can it be done? Yes, it can be done. But how we use it and how we integrate is more important. Now, we do have a lot of pilot projects and a lot of applications. For example, for the ISAC base station, Huawei already made that. It's a kind of merge rather than a full integration, because the hardware is separate and antennas are different or separate, and the time sequence is also separate, like Professor Liu said. Yeah, how much resources used for detection, and it can affect the capacity. And it's inevitable. When we first started the work on this, the people that are suspicious are the ones working on radar. So people say, yeah, you're good in communication. Why are you in sensing right now? Why do you need to distribute resource to that? I think for ISAC, there are still a lot of unsolved issues. And in terms of application, a lot of things are not solved in theory on how to integrate. Because if we integrate, we can reduce the capacity. So when we started the work, we used the reference signal to do the detection rather than the actual time sequence. We have the synchronized, or we have the pilot frequency that we can do it, but actually it's not so performant because it's not synchronized. Then we sacrificed a bit of the data domain to do it. So when you invest different resources and different continuities, the result will be different. So in the future, for full integration, the impact on the capacity is not as fixed. It changes. So, for example, there's a plane, and in order to recognize or identify the vehicle, you need to consume a bit more energy. And I agree on this by the other experts. So, for the communication sensing, it's ubiquitous. It will not be done better than radar. And finally, the identification of the situation. So in the future, for example, if you need resource, you can call more resource. And how do we do the standard for ISAC? We don't think it can be done. It can be a unified standard. It needs to have some degree of freedom. So the impact on the resource. So maybe you want to be, communication dominant or sensing dominant. You need to make the choice. And for ISAC right now, a lot of them are single station or dual station, but multiple station is the actual case. So the research is not enough. And we need to understand how much impact on the capacity. And Mr. Liu said it right. So we need to think about the current implications. Yeah, so that introduced us to the next question. So if there is some flexibility and it's ubiquitous sensing, then of course it can cause interference. For example, the complexity, and Mr. Zhang is more onto the cost. So the final cost, if we just list one frequency range just for sensing, from Mr. Zhang's perspective, the industry people, or from Professor Feng's perspective, is it more easier to realize? Because if we can use the simple use case and form the virtuous cycle, then people may recognize your technology. So what is your view? Yeah, when it comes to spectrum, one thing is about the usage of the spectrum. Yesterday, the National Authority experts said that there's, for example, the ground interface or communication and other communication, and whether the spectrum can be used for remote sensing or remote control. It needs some definition by the government. But for operators, since we're talking about ISAC, we still need to guarantee the communication users. We still need to serve them. So in that sense, it's about getting some gains or benefit, and that is the basis of 3G, 4G, 5G. And if we go up a generation, we still need to solve or serve the customers in terms of their communication. So I do want to point us the three directions: AI, satellite, and sensing. The first two are definitely serving the network more, like AI or RAN or satellite, and the business model didn't change. So if that technology is used for 6G, then people still have the same old thought: we need to make money the same way. But perception or the detection or this can be used for automotive. So we need to think about what frequency band or spectrum can we use. So for the service, since there is still communication, I think most of the resources must cover most of the users. Then for high frequency, for the millimeter wave, I think we saw that in the foreign countries, they have the terahertz. So maybe in terms of the wide coverage, it may not be that good. Maybe it could be ad hoc. And if maybe some families, they have enough, some parties, they have enough resource, they can give some to sensing. So sometimes if the frequency spectrum doesn't fit the wide application or massive application, then we can use it for the ad hoc. Yeah. Okay, Mr. Qin. I don't think the hypothesis is correct. So there is rule, right? So if it's just used for sensing, it's not communication. That it's the passive kind of positioning. It's not communication anymore. So I would say the premise may not stand. The second is just a brief sum up or addition of communication frequency used for sensing. So how do we use that? So thinking from the operator perspective, the frequency they get is definitely MT, the special frequency spectrum within the terrestrial. So it's serving the communication, but also it can be used for sensing. And there are several ways to do it. So we just do communication, and while at the side we do sensing without jeopardizing any resource of the communication. Second, they can maybe allocate some of the frequency or time resource for sensing. Or some say that we may have a big range for the sensing. So we know that in the day, communication makes more money, as everything goes to communication. But during night, there's no traffic needed. Maybe we can change it to sensing function, and it can have more value this way. Okay, Mr. Wang. So I think the two experts have said it. For spectrum, there's clear definition, and the hypothesis may not stand, but if you are given one special frequency band range, it's just one. And for the cellular communication, we can go from hundreds to thousands to even millimeter wave. So we have the chance to sense in a rough granular way remotely, or in a more fine-grained way in close distance. So we need to have the integrated sensing with different radio spectrums. I think there's more opportunity by doing this. Maybe for a store, maybe one station, we don't have for example, visual information, but with multiple stations combined, then we can have better performance. Well, okay, this is a very good question. We discussed with the military as well. They hope that they can get approved that we can use part of the network for their use. But why can't we use communication systems sometimes? Because it's about switching, it's about tracking. So I got a project from National Defense. So, okay, for radar, it's not connected, there's no protocol, and there is no resource scheduling if you want to revamp, and it's a new network. I think the biggest advantage is our infrastructure. And doesn't matter if there's the frequency, but network-based is really important. So compared to the national defense, we don't really compete on the single point or the reliability, but we can do dynamic things. And the first thing is that, of course, we're not rejecting other sensors. So ISAC, we have internal sensors, and for the external ones, maybe audio or visual, or maybe the lightnings can be seen. So I think this is about the parameters, not just single point. Yeah, I think your words echoed what Mr. Jiang said. For ISAC, it brings a lot of new business models, and the new sensors brings new opportunity for the operators and OEMs. Thank you, the four experts, and thank you, dear audience, for staying till now. And that is the end for this morning. Thank you for the organization, Professor Lu Gang. Can we say forever, wherever you go, whatever you do, I will be right here waiting for you.
看他怎么多少钻石结束的？
这个人还是挺会管的
啊，这么屌？
对，
好屌啊！他们居然准时结束了。一开始看的妈超时40分钟。
是。
他是最后那个小组讨论的时候，就一会儿就搞定了，是吧？
是的，他很快。
这个都不看了。
这个就是固定的一些内容，我就不用看了，我只要看一下这个投资的结果就行了。
哎，今天的自助餐是3天里面最好吃。
对对是的。
哎，我很喜欢吃今天很多菜我都要吃，番茄炒蛋啊，这个米线啊，红米线，那个白虾，很好吃。然后我发现一个现象，所有人，包括我自己，吃饭的时候，只要是吃饭那种大的菜，你是一边嗦往里吸，一边挖的吃，绝对会咳嗽。就所有人之间旁边那个吃生蚝的，咔一下，然后在前面有另外一个人在吃个什么东西，然后也剧烈咳嗽。然后我以前吃饭也经常这样。